that says in the Wikipedia thing.
Yeah,
So
I love talking about wartime situations because those are the most like when people's lives are on the line and like shit needs to work or else shit will break down and people will die. Like that's when it's like really obvious if they're taken into account, the curvature or not, because like we can speculate all day, on like, oh, well, maybe this, maybe that happened, but when people's lives are on the line and people might die if you make the
right,
wrong decision, and then they treat the earth as if it's flat and immobile, like
right,
that's pretty good evidence, like I always go with submarines not have never used the acoustic shadow of earth curve to hide from enemy sonar. I don't really hear many people bring up that in
uh-huh,
debates. That
Well,
one has always
speaking
been
of
really.
the parallel between water vehicles and air vehicles, that's another thing I thought of as far as like just a boat sitting on the water. When you think about it, okay, so if all the water is supposed to be spinning with the Earth, right, and the boat's just sitting on the water with all that viscosity, meaning that the boat, you have to imagine that the boat just sitting in calm water in the middle of the ocean is also spinning at 1,000 miles an hour in one direction. And with the air, I mean, I guess it doesn't work either way. Like, even if they think the air is carrying the plane without it acting on the plane like a wind, it still doesn't work because it would have to like then lock the plane into that rotation and it would never be able to fly against the spin. I mean, you can
I don't
imagine
know.
it just being like
We don't know.
one reference frame, but then two reference frames like are somehow, it's two reference frames, but then it only acts like one reference frame and it
You're
doesn't work.
confusing yourself with the words. Let's get
Oh, here we go.
Yeah, you're breaking it down in your mind, and you just went into like a max headroom glitch
Well,
mode.
without pinpointing what you think of what I'm doing, how do you explain it?
Well, yeah, reference frames are basically just point coordinate systems, and they're these point coordinate systems for which you view motion. So if I'm in a rotating reference frame, then I don't have to worry about it anymore. I'm just looking at the points around me. So if I have water, if I have land, and I have water filling a pool of water, making a lake, and I'm in a boat, and everything is moving, all the points aren't changing relative to me, then that's fine. The only thing acting on these molecules, these particles, these pieces of dirt, droplets of water, the only thing acting on them is a force that is going upward. It's called the centripetal force. And that force is equal to the radius and the velocity squared. So that force would be 0.3% of the weight of anything on the surface, near the surface.
Now,
So
Zanuck, you and I have talked about this issue. We don't need to get into it for another 3 hours tonight, right now. But you've described airplanes flying towards the equator and acknowledged the fact that it would have to somehow compensate for the difference between the original tangential velocity and the tangential velocity it needs to have when it gets to the equator. So you're not just saying it's automatically in the same reference frame.
yes, all coordinates are in all reference frames simultaneously. If I was to fly from Los Angeles to Buenos Aires, all I would have to do is travel southward, point my plane to the Buenos Aires airport, and make sure I keep it, quote, in sight the entire way. Now, obviously, I'm not going to see it, but I mean, we're going to be pointed toward it, whatever the coordinate system has been set up when we took off. We know the points along the path. We know where we have to be along the path. If we point it in that direction and continue to make sure we're on that same path, which is a straight line path to Buenos Aires, we will achieve gaining of tangential velocity, therefore gaining our momentum that we would need to equal the velocity of the surface of the Earth tangentially when we arrive.
Wait, how do you gain, regardless
There's
of all the other problems, how do you gain momentum? You can
Isn't that a
accelerate. You
violation
can
of the law
accelerate.
of conservation of
Yeah.
No,
momentum?
no.
When the momentum comes
Talking
from
about a physics
being
major.
on the Earth, right? So if just flying in a certain direction made you add that momentum to the plane, then
Yes.
they would never be able to like turn a corner because they'd still be going in
No.
that same direction, and they would have to like gauge how much momentum they added to the plane that they didn't want to have. Now they want to fly south or turn around and go the other way, and they have to then somehow just mentally subtract this momentum that they added to the plane from happening to go in one direction, and now they're headed another direction. They're like, wait a minute, now I've got to figure out that because I was going east, I added all that momentum to my airplane that I can't get rid of because it somehow works for the globe model to explain how they might be in sync with the Earth after just going in a direction.
Yeah, well, and the problem's even worse than
Well,
that
no,
too, if
Scott,
you
can I
think about
answer?
it,
Can I,
because
before you pile on?
as you gain altitude, you have to increase speed to keep up with the
That too,
ground
but let
moving
them,
beneath
yeah,
you as
that
well.
too.
Think
The
about
further you get away from the ground, the faster the atmosphere would
Yeah,
move.
so if
Yeah, there's no
you move
mechanism.
south, if you're
Can I
flying from say
answer?
a northern location like Alaska where the ground is moving beneath you, say like 250 miles per hour, and then you fly towards the equator, and you're going upwards, say you're gaining
I,
altitude too, not only do you need to gain sideways momentum while you're traveling
Yeah,
southern in a southern direction, you need to gain momentum as well for the fact that you're increasing altitude.
that
So
you're,
that's
yeah,
a
that
double
you're. It's a
violation of the law
greater
of
circle.
conservation
It's a
momentum.
greater circle, yeah,
why
than the
don't you let me
ground would
answer?
be.
It'll all be
Go
very
ahead.
clear.
Go
Both of you
ahead,
guys are
Danik.
making grossly mistaken assumptions. Both of you.
Well, you could just say that, but then you have no answer
No,
for it.
of course I'm going to back it up. I would never
I would
leave
like
you
to hear the
hanging.
answer.
Oh,
I would never call
okay?
you a
You'll
name.
be
I would never
entertained.
do anything without backing up the information succinctly, accurately, and
Okay,
representative
let's
of
hear it.
modern
Let's hear it.
physics. Okay. So you can gain momentum, and the only thing you need to do, gain momentum, is what?
No,
What
you
do you
don't
need?
ask us. You give your answer.
You
Tell
know
us.
the answer.
You're
We're saying
What
there
is
is no
required?
answer.
Hold on. What is required to change momentum?
No, don't start this
One
asking.
word.
He
One word. You
likes to
should
play
know it.
teacher. He
No,
likes
I'm
to
not
play
gonna. I'm not.
teacher
It's
as a
not
way
a
out.
class. I'm just gonna play. We're
Just
just playing
answer the
along.
question.
Okay.
You give the answers. Don't ask the
All right.
questions.
Well, I'd be encouraged if you gave me an answer because I think you know because you
No,
talk about
because he
this
plays
in the
this
right
game
terms.
where he
starting off
starts
Hold on,
acting
hold
like
on. I'm
he's
not playing a
teaching
game.
people.
Let
Don't
me
let
do
him
this.
do that. Don't let him do that, everybody. If
Let
you're
me
not
just
familiar
okay.
with Zanuck,
I'm
don't
not going
act
to
like
play a
he's
game.
teaching
I'm
by
just going to give you
asking
the
other
answer.
people.
I'm going to give you the
Just
answer.
give your answers.
I'm going to get. Stop talking, and I'm going to give you the answer. I wanted you to play along because
No, we're not
obviously
playing.
understand. I understand that you understand. I get you understand the change of momentum and all these factors. You're doing it. You're doing all the right terms. You're saying all the right terms. You're using the proper context. However, you're putting the pieces together incorrectly. And let me tell you why. Change of momentum. All you need to have a change of momentum, which does not violate the conservation laws at all, because a change of momentum can occur, and all you need is a force. Once you introduce a force, the momentum changes, and no laws are broken. No energy has been created nor destroyed.
All right, what's the force?
The force of the jet engine, the propeller.
Oh, so you're
They
saying
need
that
to
just because
change
they
their
head in one direction?
orientation then.
Yeah, so
Yeah,
you're
they're
saying,
not.
but wait, hold on. First of all, you're saying that the engines put if the pilot points the plane in a certain direction, and by using the engines, he's going to just like all of a sudden add all that momentum of
Correct.
the direction he's. But then, what if he wants to go the other way? Like I was saying, that's the
Yeah.
point.
So this is where you get wrapped around the axles. So let's just take it slowly. Like I said, started from San
Just give
Francisco,
your answer. You
going,
don't need to be slow
going
about it.
south.
Go.
We're going to point the plane directly toward Buenos Aires. Now, along the way, because the Earth is spinning and it's spinning faster tangentially as we go there, we will have to constantly be adjusting our course, and to the order of magnitude of 1 mile per hour per minute. Very, very little change to the left. Very little. Don't laugh.
Okay, so you're saying
Hold
that
on.
now you're saying that the pilot's consciously doing it rather than the
Well, no,
air doing it for him.
well, he's not going to have to consciously, because he's constantly always making sure that he's following the dot to dot to dot all the way to the destination, which is a straight line. Think of it this way. Think of it as if I'm going to find the shortest path across a moving river to a tree across the way. I'm going to make sure I'm always pointed at that river, and I'm adding throttle and always pointed at the river, no matter what the boat's doing, whatever the river's doing, it doesn't matter. As long as I'm pointing toward the river and keeping throttle, that I'm keeping a straight line to the river. Along the river, the water molecules, I've traveled a lot farther than if I would
Bro,
have.
you are.
The
I
water.
cannot
Hold
believe you
on,
just
almost
use a
done,
river
almost
as
done,
an
almost done,
analogy. I
almost done,
can't
almost
believe
done,
you're doing this.
almost done, almost done.
You have no answers,
You're
Zanuck.
traveling a lot further.
You're just acting like you know what you're talking
Let
about.
me finish the thought. It's a real simple example. Across the river, I'm traveling through a lot more water than if it was still. That's true. Think of that as the atmosphere or the air, the distance you travel through the air. But across the ground, we are traveling the exact distance between San Francisco Airport and the Buenos Aires Airport. And along the way, we are just going 1 mile per hour per minute to the east, which gives us over time, over 20 hours, 15, 20 hours, we are now adding momentum along the way equal to that would be needed to be in sync with the Earth that it's going 1,000 miles an hour versus the 500 miles an hour that we start out with.
Hey, Zanuck, real quick, just even if it did work that way, which it couldn't, even if it did work that way, how would the pilot keep track of the momentum he's added to the plane in any direction?
Did you miss the point that he's steering it and going 1 mile? Almost.
No, how would he know how much though? I mean, how does he keep track?
He doesn't.
How
All
does
he
the
knows
pilot
is
keep track?
Okay, I'll tell you.
Okay, can we take your analogy of the river really quick and can we just address the fact that in a river there's a current, and that's exactly what we're saying would have to be there would have to be a wind if the Earth is rotating. That would be the analogous to the current in the river.
Yeah.
And then if you take a boat and you try to say go a north-south meridian route in an airplane, but if you were to take a boat and just say travel across a river that's flowing in one direction and you were to just go straight, you'd be carried along with the current and not travel in a straight line. So your analogy of the river is contradictory to your own position. That's literally what you're
wind's going all directions. What if there's a wind going in the opposite direction of the momentum he needs to gain? So there you go.
I respond to please. I don't mind you scattergunning, but let me get one of your.
We're not scattergunning. You are.
Listen, I want to respond unconditional. I don't need you to pile on again. You guys are both you guys against me. So let me just you guys as you speak, and I'll respond real quick. So
Dave, let Chris crush him, bro.
Would you let me fucking respond? So, as far as the river goes, no, you are pointed to that tree across the river, and you're not going to get carried with the current because you have power to make sure that you are able to stay in a straight line between the shore and the tree along its path. If you aren't able to do that, then you didn't have enough power to actually accomplish the task.
Then you'd be in trouble, huh?
Hold on, yeah. Well, then it would be too much. But in the case of the atmosphere, which is air, which is air. If we have this progressively increasing air flow, let's say the air is one of these days where it's totally still. Everyone's measuring through Mexico, through Central America, through South America to Buenos Aires. Everyone measures an anemometer and says, you know what? Today is one of those rare days in the world history that we don't measure anyone anywhere. So that mass conceptually is going at the same velocity tangentially as the Earth is. So along the way, in order to make up the tangential velocity, we have to turn the plane a little bit to the east, and your pilot will actually be flying, and he will actually be sensing the fact that he's lagging behind, and will have to go a little bit eastward. Now that eastward direction.
What?
Changes.
Wait a minute. So you're saying the pilot's aware of this?
You got to let me finish because it's a punchline. So along the way, he just notices he makes a very small movement with the yoke, the steering wheel, if you will, to the left, to the east. And that just 1 mile an hour of speed, tangential velocity to the east will allow him over 12 hours to 15 hours to make up 500 miles an hour of tangential velocity extremely easily. And that's where you get the number from, by the way. Divide the 12 hours by the 500 miles an hour and see if 1 mile per hour per minute accomplishes it. And it does. So don't worry about it. It's not a big deal.
Don't worry about it. It sounds like you're saying the pilot would have to worry about it because he's making these corrections consciously.
All he's doing is flying a straight path. He's just flying a straight path. We've been talking about this.
What if he doesn't want us? What if he doesn't fly a straight path? What if he does big circles, Janik? What if he's doing big circles and he just wants to just fly freely and just go in big circles and he's off his path?
Hold on. Can I say something about your analogy of the river with the boat? So let's take your analogy of the airplane flying the straight path, right? Let's say a boat is crossing a river, right, that's flowing in one direction, and he's making a straight path across. He's just got one-way heading. He's not changing his steering wheel at all. He's trying to go from one side of the river to the other.
With a really strong motor.
Is there going to be a difference? Is there going to be a difference if the water is absolutely stagnant, if it's still, if there's no motion in the water, if the river isn't flowing at all? Is there going to be a difference from where he arrives at the opposite side of the bend if the river is flowing or if it's not flowing? Yes or no? Is there going to be a difference?
No difference.
Oh,
no
wow.
difference. You're saying that if he leaves and he just drives
straight. You've never been in a boat flying
against
against the current before? You never driven a boat across a river? I have many times.
Yes, a Sea-Doo.
No, I have a boat. I fly. I take it out every weekend in the summertime. We go to the river. We ski in every weekend, and there's always a slight current. Now, my skier falls, and he's sitting there. And he landed in the rocks across the shore.
Bro,
and I have to go. And I got to go get him. I would point my boat to him, and I would give a little bit of throttle, and I would tootle up to him. But you notice along the way to counteract this current, I would have a slight tilt to the steering wheel which means a vector of my thrust path vector
Okay, there you go.
is slightly changed. So the boat would actually be crabbing to the person that I'm going to pick up. I'm still following a straight path, but I'm doing it with the vector of thrust a little bit at an angle. This is the part you're not seeming to grasp for some reason. I don't know why.
No.
It's so hard
But
for me to grasp.
Because you're
there's
not
a
flying,
there's
you're
the
not
sum of the
traveling a
vectors
straight
in your
path.
example.
You're not traveling a straight path perpendicular to the river bends. You're traveling at an angle, right? So I'm a surfer. I go surfing all the time. And when there's a tide, right? When there's, depending on the tide, if I see a wave off in the distance, I don't paddle. I know how to paddle against the tide, right? I can't go in a straight line to my destination. I have to go at an angle to compensate for the tide in the same way that a boat, regardless of how powerful, I mean, you know, to a certain extent, but if you're going in a straight line, if you leave from one side of the river bend all the way to the other side of the river to the riverbed, you can't. You have to compensate for the flow of the river if you want to reach that point directly in front of you, right?
Right.
So like what you're saying, and this is all, by the way, pilots fly as if Earth is stationary and level. They don't compensate for Earth's spin when they're not tilting their wheel. When they're flying from, say, Alaska to California, or they're going north to south meridian flight, they're not flying in turn. They're not plotting in their head, doing equations, going, okay, well, we know the Earth is going to be gaining speed. I know the ground is traveling at 250 miles an hour at my departure, and that at my arrival, it's going to be going close to 1,000 miles. So I got to gauge, and I got to turn the wheel the heading this way. If your argument hinges on the fact that the engines are providing power, well, then those engines would need to be orienting themselves to compensate for the curvature of, the rotation of the Earth as the speed of the ground gradually increased beneath them as they headed south. So that's not what they're doing. So the fact that they're not doing that they don't constantly have to correct and adjust, and again, that's only part of the problem. The other problem would be increase of altitude would also require them to increase their speed, because that's as you increase the radius, the tangentially the further you get from the center of the Earth, the faster you're going to be going. So they would have to take that into account too. None of these corrections are made, and
Right. The
the
Blackbird is a
pilot
good example.
either consciously has to be doing it, or I mean, there is no answer. I mean, but their answers are like they go back and forth between, well, the pilot would just have to make all these corrections, but then he wouldn't have to worry about it. He just have to follow the ground path. But then the atmosphere would be pushing him, so he wouldn't have to worry about it. Well, is it the atmosphere, or is it the pilot, or is it the ground path? None of those even would make any sense,
let's
because
take a simple
the speed.
example.
Why don't you let me finish the? Hey, 5 minutes
you said
now.
that
I haven't said a word in 5 minutes.
Let's take the engine completely out of it.
I haven't said a word in 5
Baumgartner.
minutes. Can I say something?
Wait, no,
Yes,
Zanuck, just to let him finish with his point real quick.
Can I? Can you go ahead and I was gonna say we could simplify this and take the engine out of it and just go with Felix Baumgartner's Red Bull jump.
Yeah, that's the
he
other
didn't have
thing,
a motor on the balloon, and he was going up, but the fact that every foot that he gained altitude would have required him to increase his speed to keep up with the rotation of Earth, because as you gain altitude from the surface, you have to increase your speed to keep up with the rotation of Earth. He landed, by the way, 55 miles east of his departure point when he landed, not west. So the Earth was supposedly spinning beneath him, and he was keeping up with the rotation of the ground. As he gained altitude, he had to also gain sideways momentum to keep up with the moving ground beneath him, and he didn't have an engine. So how does that work out in your whole paradigm of you need a force to keep up with the to make sure that it's not a violation
given the
of the law of
danger
conservation
involved,
of Earth?
there would be no argument here. There would be one precise answer. Everybody would know it because they fly in planes and they're safe, and we know we land safely. And there would be one answer that is patented, that this is exactly how it works. But they have no answers. They have zero answers. But they have, just follow the ground path, or just the air would do it for them, or it's
been 7 minutes.
conservation of
Let me know when
momentum.
you're done.
Even though there's a tangential velocity change, it's just the conservation. I mean, you have all these like possible like ideas that make it seem to work in your head, possibly, unless you just are defending it for no reason. But there would be one answer, because pilots have to know this to land safely.
If
they
you want
only
an
treat it
answer,
as stationary.
Can you address the
It's
Felix
been over
one
5 minutes
specifically,
now.
please?
I haven't said a word in 5 minutes. Can I say something?
Go ahead.
Yeah, go ahead.
I mean, it's not cool, dude. Come on. I mean, it's a good conversation, and you're asking good questions.
Yeah.
Let me say the answers. So I have answers for you. And yes, when you're flying southward or across a river, would use a vector of thrust, which would actually cause the boat to crab and be exactly following a straight line. If you have enough power to, you mentioned paddling and surfing in the ocean, which I do as well. And yeah, sometimes you can't paddle fast enough to keep up with the tide or a current. And that's fine. You just do your best, wait till it calms down, or you go against it and try to get a different angle and try to get out of the riptide current, and you're fine. We're not talking about that. We're talking about flying in an atmosphere and flying over a sphere where there would be a tangential velocity change as you go south, as well as wind. There's no difference about how we deal with wind in an airplane as a pilot, myself, when you're flying southward, how you deal with what's happening from point to point. And all you're doing is making sure you're going from point to point. Whatever is happening to the wind, and it happens all the time where you go, geez, to follow this path, I got to go more rudder, more. Sometimes I'm amazed, like this much rudder, really? Do I have that kind of a crosswind? And then finally someone says, yeah, we got like a 40-knot crosswind right here. It's crazy. And you're crabbing to try to keep path. Sometimes you give up and you just try to go around because you can't do it. Maybe the thunderstorm cloud around you that's causing this crazy current. But the point is that you do point toward it, and if you have power, you want to go straight, and you will basically crab to go through the. And it's usually not a lot. If you're going 200 or 300 miles an hour and you have a 30 or 40-knot crosswind, you have it's not that big of a crab to do that, because all you have to do is be making up 40 miles an hour, and that's you can go 40 miles an hour at full speed with just a little bit of yaw.
Here. Are you talking about wind? We're talking. You said that you said to keep up with Earth's rotation.
Both. There's no difference in how we deal with Earth rotation and wind, and all of it is making sure you go point to point. If you're going southward and you were a ballistic, hold on, I'll give you an example. If you were a ballistic, you said you took off, you're going to set your rudder and ailerons to be straight. Figure out a way to do that, and you don't touch anything. Like you have one of those autopilots that's not an autopilot, just kind of fixes things and it locks things in place, like with the set screws. You just let the plane go. It'd fly like a ballistic. And you would see it start drifting off by maybe.
Okay, so how does that work
over 25 miles? Over 25 miles, you might be off by 100 yards from a target way 25 miles away. Maybe down on a bridge. So you can actually account for that along the way by just turning the rudder a little bit to the left or right, so you stay on a straight path. It's a simple adjustment to make to do that.
Okay, how does that work with Felix Baumgartner, who didn't have an engine? It was literally a balloon that raised him up to, what was it, like 125,000 feet, I think it was. So he would have had He would have had to increase his tangential velocity, right, as he raised, and then lower it as he fell. How did he gain that extra momentum?
But just real quick. He's going to Baumgartner, not but as another example. It's not like you gave a sufficient answer for the other points at all.
I did.
That's not to say okay, but
no, I did.
No, exactly.
And I'll take the Baumgartner. First of all, Baumgartner is not traveling over the sphere. He's not moving, and that you need that for a correlate to happen. But he's going up. If you're saying he's going up, and that is now we're also having a slight correlate effect as well by going up, because everything directly above the sphere is going to have to be going at a higher tangent velocity to be keeping up with rotation. And I would agree to that.
That's my question.
But we're talking about how. So he didn't stay in one spot. You know this, right? Up at 130,000 feet, there was how much of a deviation of tangential velocity between the surface? Do you know? You would make that a point.
Why ask that?
Because you would if the air was still, which wasn't even still. If the air was still and there was no air movement at all but like a column of air, then there would be, as you're saying, this change in tangential velocity. And
it was a 2.5 hour ascent. It was a 2.5 hour ascent, and the ground beneath him was moving at nearly he was in Nevada, so it would have been, let's say it was moving at 800 miles an hour, and it was a 2.5 hour ascent. He should have landed somewhere in the middle of the Pacific Ocean if the ground was rotating beneath him, but he didn't.
You see how confused you are?
How was he able to keep up with the ground beneath him? How did he get in?
I'll answer. Just God, get it.
But
first of all, you've confused this conservation momentum grossly. Let me straighten it out for you, because the point you made was actually a good one. As you go up from the ground, there should be a lagging behind versus the spin, because you're going higher and in a higher circle, a greater radius, which would mean you're going to have a loss of tangential position due to the same tangential velocity. Even if you don't gain any momentum going up, you'll be positioned versus the ground. That makes sense. If you're thinking that because he's not attached to the ground and suddenly you're changing reference frames and now he's going he's not moving, and the Earth should be spinning under him by 800 miles an hour, you're grossly wrong. Because no, when he left the ground, he was going 800 miles an hour tangential velocity. He was going 800 miles an hour tangential velocity when he got to the top due to the conservation law. But however, the point at which he's resting at before he jumped is at a slightly fast, let's say it's 1 or 2 miles an hour faster. And the truth of the matter is, he wasn't directly above his ascent point when he jumped. He was, I think he was 50 miles off over the 2.5 hours, or 20 miles off.
East, bro. The Earth was spinning the other direction. He should have landed west.
No,
if that's your
should have.
argument.
No, that's not true. We don't know which way the wind was. The wind is a more dominant factor than this 1 mile an hour or a quarter of an hour tangential velocity differential between 130,000 feet, which is only about 25 miles, by the way, out of a radius of 3,950 miles. So it's a very small percentage. That in fact, they're directly proportional. So what is 26 miles as a percentage to 39.59? Do you know what that is? The answer is off the top of your head?
Why are you, dude? You're just like
it's not a valid point.
25.
Comparing the tangential velocity to winds and whether
0.63%.
one would affect it more or not. It doesn't do you any good.
I was giving the answer. You're adding chitter chat.
It's 0.63%, which is about, if you multiply the 0.0063 times 800 miles an hour, if we're using that as the initial speed at the ground, it's a difference of 5 miles an hour at the top.
Okay, so 5 miles an hour.
So he's going.
Hold on,
5 miles an hour faster.
Hold on.
He's going 5 miles an hour faster at the top, right?
Hold on.
Go ahead.
5 miles an hour over how many hours was this ascent? 3 hours.
Well, his ascent was 2.5 hours.
Okay, so he should be 10 miles off. But in actuality, he was like 20 miles off. And I heard someone say that it wasn't even in the wrong direction. And that's fine too, because you know what? The winds are more dominant. The swirling winds in the direction of the wind is the most dominant factor, not the Coriolis in this vertical Coriolis in this respect. So that's nothing. There's nothing wrong with that. There's nothing that's amazing about that whatsoever. And it certainly wouldn't have been, 800 miles off, because that would say that as soon as he left the ground, he lost all his tangential velocity. All his momentum.
I got a better example
happen.
for you, Zanuck. Since the first one, I agree. Listen, I agree a little more with you on the second one, simply because crosswinds have a greater effect than 5 miles an hour does, but it's unpredictable. So, like, I am still sided with them on this, but I will say your point is better on the balloon example than it was on the plane. But let me ask you this, okay? The SR-71 Blackbird flew across the country in an hour, okay? If that thing is flying north to south, which it has been used in missions, flying in all sorts of different directions, if that thing is flying north to south at 2,900 miles an hour, over an hour, it'll cover a distance of 2,900 miles, okay? Let's just round it to 3,000 just to make the math easy. So it's going to cover 3,000 miles in an hour going north to south in a straight line, okay? The distance from, let's say, the northern United States to Texas, anybody got that number on hand? Because I want to see where he would end up.
He'd be in the middle of Mexico.
Yeah, in the middle of Mexico. So, what would be the difference in velocity that would change between the surface of the Earth moving rotationally at the north point and the south point? How many hundred miles an hour?
You could do it simply by doing some.
Yeah, I was going to do a ground speed ground speed calculator,
roughly 100, 200 miles an hour, maybe.
Yeah, I would say at least 200 miles an hour, right? So 200 miles an hour in an hour. Okay, he changed 200 miles an hour. Okay.
Yeah. So 200 miles an hour in an hour. What kind of acceleration rate do you need? And that's how you calculate the Coriolis force, by the way. So this is actually a very good exercise, because of the Coriolis force, which actually is greater as you go faster, which is contrary to common sense or intuition, because if you go faster, you'll eliminate the chance of the Earth spinning under you that fast. You know what I mean? But it's not an oxymoron. It's kind of a counterintuitive way of looking at. I had a hard time with this, by the way, in physics, because people say, "Why would that? If you go faster, less Coriolis force, because if you shoot really fast, there's not time for the Earth to get underneath you, right?"
I understand vector sums. Don't get me wrong. Hold on. I understand vector sums.
Then you understand that for me to go faster and be more instantly at a higher tangential velocity, that requires a force. That's why the tangent. That's why the correlative force is greater.
Let me just throw my point out there because I think
I
you're getting there.
get your
But
point, by the way.
well, okay. So you understand the difference, but what you are suggesting is that in order for that man to get to his destination efficiently, and the simplest way is he wouldn't be pointing straight south. He would be flying at a diagonal the entire time. And just so you know,
is heading is what you're saying.
the reason the Blackbird is a good example is when you're flying at those speeds, you are not changing direction. You are taking a dead reckoning and you are pointing it and you are going, because that thing creates so much drag, even just flying in a straight line, that the outside of that plane superheats. Okay. It's like a flaming missile.
Drag does not cause it to hot. It's the compression of the air in front of it which causes it to get hot. So get it straight.
Yes, but they
and
don't change.
Drag too, by the way, but you're right. So all
they don't change direction when they're flying.
Well, yeah, they do. They
at 2,900 miles an hour.
Because if they're flying north to south and they're flying at 50,000 feet or 60,000 feet where they fly, then yes, it will fly in these jet streams, which could be going 200 miles an hour, as a crosswind. So they'd have to have a ever so slight churn. Now, this is the point you wanted to make. This is very good. We could use it two ways. We could say we have a 200-mile crosswind the entire time we go through an hour, or we have a Coriolis effect, which ends up with a net, which is a little different because it's progressively going from zero change to a 200-mile-an-hour change. So what would it take as far as acceleration to go from 0 to 200 miles an hour tangentially east to west to make up for it? And that's a simple calculation. Can you give me the answer?
Are you saying in terms of time?
In terms of acceleration, what kind of banking how many G forces to the left, to the east would I have to make up the tangential velocity difference, which would be more like 150 miles an hour? But let's say it's 200 just for the sake of. We're going from America to the middle of Mexico, 3,000 miles. We do it in an hour, and the tangential velocity, let's say it's 200 miles, 200 miles an hour. So over an hour, regardless of what we're doing, the numbers are fine. 200 miles an hour, tangential velocity difference, flying for an hour. How much acceleration would I need to accelerate to that velocity, 200 miles an hour? You can plug in a calculator online if you'd like. It's a simple equation.
It's 3 1/3 miles an hour a minute.
Oh, good, you did that. So that's 3.5 miles an hour per minute. That's like walking speed. So all it takes for that SR-71 to do is turn
it's a constant acceleration. It's not just once. It's the entire time.
You can do it the entire time.
If you made it equal, which you would, because you're getting a bearing and heading in it.
Well, no, it's not. It is.
The point is he wouldn't be just bearing south. He'd be bearing south. Okay.
Well,
east.
You gave me. It doesn't matter. You gave me the right answer. Now you can put it in terms that you can feel more comfortable with saying. Either give me a force, which would be a constant acceleration along the way. You gave me a 1.5 mile per hour acceleration per minute. That's not
3.33.
That isn't that's not a G. That's not an acceleration, because acceleration will be squared, right? So it's just it's a linear change. So it's not. It almost isn't even an acceleration.
What?
It is. It's an acceleration, but it's very slight. It's not like 1 meter per second. We're going 1.5 or 3.3 miles per hour per minute. So that works out to be 200 miles an hour by the time you get there. And you can now give me the G calculation of what you'd have to put on the airplane to make that turn. And it would be nothing that could even be felt. The acceleration to the left, for example, if I had a 1G acceleration, you know that a 1G acceleration in a year would be light speed. You know that a 1G acceleration in 6 seconds is 60 miles an hour. I mean, these are the things that are, you just have to think about this, that going south and getting 200 miles an hour of tangential velocity added to the momentum with respect to the inertial reference frame, it will not be that much of an acceleration.
Bro, the point is that the azimuth angle that he's shooting to get his bearing is drastically different from the one he's shooting, not accounting for that. And when you don't have there's no real life examples of a pilot when they take off and they're shooting a straight line path to their destination of them overshooting it by X many degrees off to the left to account for the rotation of the Earth flying south.
That's no different than if I had a 1.5 miles per hour per minute crosswind along the way. There's no difference at all.
What do you mean no difference? What do you mean no? Hey, Zanuck, you told me that the point I brought up was that that you've ever heard as far as the defending, trying to defend the globe. And if he's going west southwest, going the opposite direction of the of the eastward tangential velocity that he would need to gain, which isn't even possible anyway. Even if it was, he's going west southwest. How's he gaining eastward tangential velocity?
By pointing straight at it, knowing the dots
Straight at
below.
what?
Hold on, knowing the dots beneath them, knowing the coordinates beneath, and just make sure he follows that coordinate system, and he will
Yeah, but
effectively.
he's going west southwest.
Can I
How's he
finish?
gaining
Can I
eastward
finish my
momentum?
sentence? Do this. You do this to me all the time. A chance. Say, follows the straight path line, and along that straight path will be a slight eastward rudder setting, which will allow
Wait.
him to accelerate and make up that tangential velocity, thus gaining momentum along the way.
Do you guys
Not
hear
funny.
this?
You've
As
been doing
he's
this. You've been
headed,
doing this for 3 years now.
He's strictly going west southwest, but you're saying there's some slight eastward thing going on?
No. He's pointing it slightly eastward. He's got a vector
Wait,
eastward, but he's
no,
following.
he's west
He's going
southwest.
directly. Hold on. Just stop. He's going directly point to point. If he's going south southwest, he is pointing his airplane southwest, and as he's flying, he has the plane not quite pointed that direction, a little bit crabbing to the east along the path.
Okay, hey Zanuck. No, hold on. Zanuck, you want to know why I also like the Blackbird example? Because not only would you need to account for that crosswind that you say, or the difference in tangential velocity of the differing change of the rotational speed of the Earth, but also I've got the math right here for you as well. If this thing travels 2,900 miles across the surface of the Earth in an hour, do you know what the amount of curvature that you encounter across 2,900 miles is? It's approximately 5,008,335 feet. Now, we can divide that by 60 to see how many miles or how many feet per minute it would be, which is 83,472, and then divide that by 60 to see how many feet per second it would be, which is 1,391, which is just a little over a quarter mile. So approximately a mile every 4 seconds. That Blackbird would have to dip its nose down and go downwards towards the surface of the Earth a mile every 4 seconds, or
All right.
15 miles of a minute.
You ready for the answer? The answer is no, and this is my favorite topic. Something I also know very. So an airplane flies with respect to its center of gravity, angle of incidence of the wing, and angle of attack of the wings, and the vector line of down. Okay, so along this path, that vector of down, it's constantly changing. It's not parallel. So there's no dipping in the nose. The nose will be slightly raised, as most of these airplanes are flying high speed. The faster the SR-71 flies, the lower the nose gets, by the way, but it still would be a positive angle of attack. And so it would not have to dip. It would just follow the curve because the atmosphere is curved. Vector lines of down are changing, are not parallel.
If you say that that's true.
Now let me give you an analogy to add frosting to this statement that is very true. If you understand it, it should be not even a question. That's a lousy argument. I think better than that. I can tell you're smarter. If we had a control line airplane on the end of a string, the ones you fly when you're a kid, and it's attached to the wing, two lines are attached to the wing to the elevator. When you fly around a circle, that plane is not having to turn. It automatically follows the circular path without having to turn into you. No controls whatsoever because of the centripetal force acting on the wing and the CG of the airplane acting on you outward. So the plane will naturally just follow a circular path. You see the ones flying in the model in the souvenir shops. They fly around stuck to the ceiling and doing circular paths. They're not steering. It's all done by the centripetal force. And that centripetal force is its weight, and it is the constant change of direction of the vector down along its path. So there's no need to dip the nose, and it would be following the curve, but there's no need. It would basically feel like it's going straight because it's flying a geodesic path.
Quick question. It's going to be 2 points. Okay, just confirm this first point. That would mean that the same airplane flying at two different speeds, one half of the other, right, would be basically encountering curvature at a different rate and angling its nose down at a different rate, right?
No change at all. Think of the control of an airplane. No matter how fast I fly it, no matter how slow I fly it, as long as it's flying, there's no change in that setting of all the ailerons and the rudder to make it fly around in circles. Always will be directed toward me. My profile of the plane would be the whole plane facing me, tied to the wing tips, because the centrifugal force is the line keeping it from flying away, and the centrifugal force is it wanting to go outward, but it wouldn't change no matter, even if that value goes down or up. The faster it goes, nothing changes. It always be flying around in circles.
So
How fast that plane goes, it always flies around in circles. No different than what you just laid out.
So second part, in this model that you just gave, what would be the how much of a difference would you see flying this plane at the same speed across a sphere or across a flat plane?
There's no difference between what the plane feels or how it's. You're flying level. It'd be very easy to fly level. Assuming it's the same ease of flying level.
So there would be no difference.
No difference.
As
None.
okay. So this 4 miles, this mile per every 4 seconds. Okay, 1,300 feet a second. Okay, the ground is. Don't just let me finish. The ground is curving away at 1,300 feet a second, right? You're saying that that's like automatically accounted for?
Not automatically, because down is a 90-degree. Think of it as a 90-degree angle to the horizontal level flight. The orientation is horizontal.
But the entire time it's moving, the orientation is attempting to change.
For every foot, every inch, every millimeter it moves, every mile it moves, it is tethered with this magical thing called the weight of the airplane, this gravity.
But I just asked you if the speed at which it travels would alter what it encounters, and you said no.
No, it doesn't.
It would have to, because the attempted.
No matter how fast you go, the plane is tied to a CG. This CG is about 1/3 back from the front leading edge of the wing. If you were to put your finger on that plane at the fuselage at about 1/3 back the leading edge, the plane would balance. And if you're keeping it balanced while you're going over the curve, it's not going to change. It's not going to flip up or down. It's going to stay balanced no matter where I move on the sphere, because that vector of down is always going to be not parallel. It means it constantly will be shifting.
The vector of down would feel different. It would be to a different magnitude depending on the speed you're traveling, because the speed you're traveling dictates the rate at which you're encountering the downward dip. So it would hit you faster or slower depending on how fast or slow the plane's moving.
A flat Earth, but then there's like pressure altitude.
I just know that you're not looking at clear eyes right now. Think about why planes fly, how they fly with the CG, that relative to the downward direction and its weight following that downward direction, and that vector always changing. Put on a piece of paper a curve path over the Earth with the presupposed vector of gravity. We're just trying to understand the model. Right now, you're not understanding it. There's no difference how you would control it or how the plane would fly if it's flying over the geodesic path, which is basically a straight line path that's curved, or over flat Earth, where down is always parallel and you're flying straight. There's no difference in how you control the plane, because the plane flies based on this direction of down and a right angle to the direction of travel of the plane, this level flight. So you're just not thinking. I don't want to argue because you're just not getting it. I know once you look at it closer, you'll think. I guarantee, once you look at it closer, you will figure it out. It's not that complicated,
bro.
And you're basically just saying that that it's, you treat the Earth as if it's flat and stationary when you're flying a plane. I get it. Except for you're also saying that you have to lead your heading, which objectively pilots don't do. I mean, Witsit even has a video on his channel of him interviewing a pilot where he asks him, how do you fly the plane? And the pilot literally says, as if the Earth is flat and stationary. So
I
they
would say
don't
that.
lead their headings. That has never happened. So you're wrong on that. But really, really quick, just
You're
because
not
I've been
wrong
waiting a
anyway.
while to ask this. This is kind of a follow-up question. You can go back to the topic that you were talking about, but just really quick, because I'm gonna have to go in a little bit here. This was kind of like where I was going with my follow-up to the Felix Baumgartner. So that was a mere couple or very, very small fraction of the radius above Earth. Now, I've never actually gotten a straight answer from a Glober on this, so I'm actually really grateful that you're here. I'm honestly asking this. Do you believe that, as they say, that the atmosphere extends beyond the moon, right? You believe that?
I don't know. I mean, I know there's particles from our atmosphere that have shot off into space and are
Okay, but you believe
around the Earth.
that Earth is velcroed to you believe that the atmosphere is like velcroed to Earth, right? So the atmosphere moves and to keep up with the ground. That's basically your argument, right? The atmosphere
Yeah, I mean,
moves
yeah,
around and there's no lag, right?
no, there is some lag, but there's other forces that are. I mean, my God, we have an atmosphere that's heating and cooling, and there's thermal convection currents, which are related to
Well, we
along
know
with
that the
pressure
upper
differentials. Hold on. So yeah,
but
it's roughly attached to the Earth, and it doesn't go out that far with respect to percentage of the radius, but it does. And as things go out farther and farther, they become less and less attracted to the Earth. There's a higher and higher tangential velocity required to keep up, so they would lag behind slightly. But
Bullshit is that.
we also see other forces acting on solar, also adding speed, detracting speed. The Coriolis
okay.
effect.
So
All sorts of forces. There's a lot of forces going on.
You want to say
we have
thermal
the upper
compression currents?
There's only
layers of the atmosphere
Bullshit.
traveling. We have super rotation. Are you familiar with that? We have the upper layers of the atmosphere
yes,
traveling allegedly
yes.
faster than
I,
the ground.
I alluded to that, and above 60 miles, there's only a few atoms every like couple hundred feet. I can't remember the number, but it's. Think about one atom of gas of your atmosphere at 60 miles. There's very few particles. They're very very far
Okay, but are
apart.
those so that my question that I've never actually gotten an answer for, so maybe you could kind of help me out here is in your model with the moon, because if you look it up, they will say it literally like says that the Earth's atmosphere extends beyond the moon. That's what they claim. So in your model, how fast is that part of the atmosphere moving? Like,
It's not.
is it rotating with
No,
the Earth to keep up with the ground, or how fast is it
no,
going?
no. They're just talking about parts of particles, atoms that have left the Earth wandering, maybe get
Uh,
intercepted by
So
the
how
moon's
fast is it going?
gravitational field. But no, once you get above 60, 70 miles, I mean, it's much less. It's still there. It's still motion, keeping it. But if you have a terminal velocity or a escape velocity speed atom, it will escape. So the hydrogen atoms can actually leave the uh, the atmosphere. But there's so few of them. It's not even as far as with respect to a percentage of the atmosphere
I don't
itself.
care how few there are. I'm
There
asking
are
how fast they're
there's a
going.
few. They're going fast, and some are going leave the orbit of the Earth and go off into space forever because they have faster than escape velocity, and some actually are following the Earth in the atmosphere. It just it gets less and less dense as you go outward.
So
But the
the question
gravitational
Okay,
though
field,
is,
you gave a lot of answers there, but I'm just okay. Like let's just take. So you believe like you said you said you do believe in fluid dynamics as it applies to the atmosphere, right? So you believe that Earth is spinning, and then as you increase altitude, the atmosphere should lag behind the ground speed, right? Because it's not physically attached to the ground. You believe that, right?
if there are no other forces, yes.
Okay. So in like when you say like you get out to the moon, right? Those they claim that those are still atmosphere, right? That's still atmosphere. So you would say that those would be lagging far below the ground speed. Those are not traveling, say at the equator. If you were to go out, increase your altitude from like a location on the equator all the way out to the moon, right? 237 or however 237,000 miles away, are those air molecules that are part of the atmosphere? And I don't care how few there are. Are they traveling less? They're traveling much less than 1,040 miles per hour, right? In your
Well,
model?
when you get that far out, and the moon is nearby, there's a point about 20,000 miles from the moon where these particles will be in a equilibrium. There's no pull either way, so they're not. The Earth is not. And remember, these molecules that are spinning have a tangential velocity, and in a direction as well. As you go higher, the curvature, the direction following the orbit for the atmosphere itself. That's all going to change, and they have to have some incentive to continue to follow. That is caused by other molecules they run into, or atoms they run into. Molecules, they'd be too heavy to even leave the atmosphere. Only atoms are going to be out there, single atoms. So, or particles, large massive particles, and they're going in all directions, and they're not orbiting the Earth out past them. They're not even orbiting halfway to
so
them.
so with so like you agreed, you said that you're familiar with super rotation at the higher ends of the atmosphere. So those are
Yes.
actually traveling much faster than the ground, right?
A
They're
lot
traveling
faster, yes.
they're traveling faster than the ground, okay? So and then at what point in your model do they stop traveling faster than the ground and start, because you said you believed in fluid dynamics, right? So Earth is rotating, right? The physical rotation of Earth is happening, and then like as you increase altitude from Earth, the atmosphere should be lagging behind the physical rotation. But you're saying, oh no, there's lots of other forces, that are keeping fluid dynamics from taking place to such a great degree that at the upper layers of the atmosphere, they're actually moving faster than the Earth, right? So at what point because if you believe in fluid dynamics, if you think that that's a real thing, then where is that taking place in your model?
Yeah, you hit it right on the head there. There's other forces, and those forces only are very, very slight, and they act on very small particles that are very far away from the surface of the Earth. And that happens
Well, no, they can't be very slight if they're causing the upper layers of the atmosphere to rotate faster than the Earth itself. So
whatever layers of the atmosphere you're talking about. The stratosphere, no. Thermosphere, the thermosphere. In the
I
thermosphere.
forget which one here.
Oh,
I mean,
in the thermosphere. So it's and those
okay, so
particles
atmospheric superrotation is where, let's see, it takes place. I don't know.
in the thermosphere. I think. I don't know. You keep on asking. Everyone always asks for like, well, what point does this happen, and where does space end? Where does space begin? And it happens. I mean, these are good questions, but it's not that way. It's a very gradual. It's a very.
But you're claiming
it's a very
that
simple concept of a gradient.
He tries to make himself sound
You're
smart.
claiming extra forces. You're claiming that just all these forces nullify fluid dynamics, but then you're also not specifying the forces. So if the Earth itself is rotating at 1,040 miles an hour at the equator, and there's super rotation of the atmosphere, what is causing the upper layers of the atmosphere, this super rotation, to move faster than the Earth itself? That would be my question.
Yeah. They're saying that it is the solar things that actually kill us.
So solar
winds, yes.
Solar winds.
Solar winds.
How do solar winds nullify fluid dynamics?
How does it not? What do you keep on moving? What do you mean when you say fluid dynamics? How is anything
Fluid dynamics is that, like, think about a good analogy would be a blender, right? So as you are, like, if you look down in a blender, the blades are moving super fast, right? And then as the liquid, which is not physically, they're fluid, right? That's fluid dynamics. The liquid in the blender is not spinning at the same speed of the blades on the outer edges of the blender. As you move further away from the center where the blades are spinning, the fluid is going to be spinning slower and slower. That's fluid dynamics.
No, I know
right?
what fluid dynamics. I know. I've taken the class. I know what fluid dynamics. I want to know.
Okay, so if you know what it is, then how you claim that solar winds are nullifying the effects of fluid dynamics? You're saying that fluid dynamics doesn't apply.
Let's go back to your blender.
So how does that work?
Let's go back to your blender now just for a second. Nothing is going against fluid dynamics. If I'm blending a milkshake and some of these particulates stick to the glass and they don't move anymore, well, now there's a force holding them, fighting off the fluid molecules that are hitting, or particles that are hitting into them, and they're not breaking them free, and it's not breaking any laws of fluid.
Why are you bringing up the glass?
The glass has nothing I'm just saying that there's ways that things don't follow this.
Hey, are you arguing that are you arguing for the firmament right now? What's going on
so
here?
At the top
Zanuck,
of
you're disc
like the glass, let me finish. So like the glass, when we have solar winds that are accelerating these particles in a direction that's ahead of the Earth's rotation, this is only a theory. This is one of the reasons why they think that there is super rotation because of solar winds. There's other theories as well, but these particles are being accelerated, given energy to by the sun and the solar winds. These gamma rays, these high energy rays, and ejections from the sun hit the Earth and accelerate the upper atmosphere to go even faster.
In just one direction?
In just one direction, yeah.
Why in just one direction?
Just like Coriolis acts in one direction for the.
No, it doesn't.
Why does the jet stream does go eastward, both north and south? Why is that? Because everything in the northern hemisphere was deflected to the right, and everything in the southern hemisphere is deflected to the left, and that makes everything in the jet stream. There's other reasons why there's other.
Yeah, but his point, but the point about fluid dynamics.
Let me just finish. Can I just finish the final? Is that's why those jet streams that are both in the southern and north, both
in opposite directions.
Ahead. Hold on, I'm almost done. Ahead of the Earth's rotation. Thank you for.
So okay, so then the fluid dynamics. The fluid dynamics, the point, first of all, yeah, you have jet streams that go faster than the Earth. So how does it go in? How does a plane go inside a jet stream and then come out and then be in perfect tangential sync with the eastward tangential velocity of the Earth? Also,
that's an easy question.
Well, I'm just saying. Well, there isn't an answer. You could just gestalt up and act like you have an answer.
No,
with
I
the
have
confidence
an answer.
that just is basically gaslighting everybody. There is no answer. Go ahead.
No, there is an answer. My God,
how does it get in sync with the Earth again? If it's going 200 miles per hour faster.
I've flown. One time I had a flight to the west. There was a massive high pressure system that was building out in California. I got from Hawaii to San Francisco like in 4.5 hours. Normally it takes like 5.5 hours. It was like an hour faster because they were flying in 150 mile an hour jet stream all the way to just happened to be the right path, and it was at our tailwind the entire time. Now that's not a problem. We could be flying the other direction, or I could be flying through it north or south.
Just saying
he's asking you pop out of the jet stream at a perpendicular direction. How do you all of a sudden? Because instantly, as soon as you pop out the jet stream, you're at a 200 mile an hour offset from the jet stream in a perpendicular direction.
It's not like you're thinking. It's like what was that movie with the little?
Well, I'm just repeating what you said.
Nemo,
it's 200 miles per hour faster than the spin of the Earth.
Guys, come on, man.
The jet stream's going 200 miles per hour faster than the spin of the Earth.
Are you serious now?
Let me finish.
You're just going anecdotal. You're just going with anecdotal little like things.
Those anecdotes.
Thank you. It's not like Finding Nemo where the turtles are in that little jet stream in the water, the hyper fast, like almost like a jet stream, and he like jumps off.
I never saw this movie.
Oh my God, it's impossible.
Dude, you're just like talking so that you sound like you have an answer, but you don't have an answer.
I do have an answer. My God.
Fluid dynamics is a problem.
Let's be honest. Let's be honest here, bro. You're talking like just you're saying a bunch of stuff that just is nonsense. In terms, well, I mean, look, I'm not trying to lean on ad homs here, to be honest. I'm just like, look, you're claiming that airplanes lead their heading. That is not how any pilot flies. They don't take into account Earth rotation, and you're trying to convince us that they do, so much so that when I brought up the river in a boat, you claim that a boat crossing a river it's the exact same as if the river is moving as if it's not moving. That's just nonsense.
It is not nonsense. So let me explain.
It is nonsense. That's nonsense.
Can I explain?
It's not. It's no. One has a bearing change and the other doesn't.
Come on, guys. Let me respond.
You already said you go diagonally in your boat, but like if the river's not moving, you go straight. So that's a difference. That they're not the same.
It's not going diagonally.
Yeah, what would be the difference, Zanuck, real quick? What would be, just explain to them, this lands. Wait, real quick. How would you train a pilot to fly over a stationary Earth as opposed to training a pilot to fly over a spinning globe Earth? What would be the difference?
There's absolutely zero difference because of
there you go.
Then you're contradicting yourself,
bro. There you go. That's a total contradiction because you're talking about leading. You're talking about leading.
You guys aren't letting me talk, man.
So many dynamical differences.
You guys are talking
you're saying you're leading. You're saying pilots have to lead their heading on a rotating Earth, but then you're saying that there's no difference between a rotating and a spinning and a stationary Earth if you're flying. Those are contradictory statements. You're contradicting yourself.
No,
objectively,
because you can fly over a flat Earth and have crosswinds. And that same exact pilot interaction with its airplane versus the direction of travel and its destination is no different than flying if you had no winds and a Coriolis effect. There's no difference in the chain.
Wait,
can I finish the fucking statement, guys? You notice I'm saying every time we talk, I'm saying.
Yeah, because crosswinds and the Earth spinning are two different things, Zanuck. Period.
You can't, bro. You can't say, okay, if you can't say pilot, there's no difference between how pilots would be trained on a stationary Earth compared to on a rotating Earth, and then say that pilots on Earth all act as if there's constant crosswinds. That's clearly a difference that they would have to be trained on. They would have to be trained to fly as if there's constant crosswinds in one direction only on a rotating Earth. That's a difference. So how are you going to say that there is no difference between a stationary and a rotating Earth? You understand our point?
Because there wouldn't not be a difference in how you control the airplane. It wouldn't matter whether you're fighting a crosswind or a Norris effect. All you're doing is trying to fly from one point to another. Crossing the river is a great analogy because if I have the power to do it, I'm going to point my boat directly to that tree, and I'm going to be going toward it, even though my back end will be slightly tilted off to the left or right, depending on which way the stream is going. And with the power, I will allow myself to travel a path that would be a straight line from the shore I departed to the tree across the river, even though the boat was slightly tilted. That's the same thing a plane does in a crosswind. Coriolis is called a crab type of motion across the surface, where you have a yaw angle.
All right, okay. You're just like describing what you know about flying as if it's an answer. But let me
It
just
is an
ask you this,
answer.
Zanuck.
Exactly.
It's no,
Exactly.
it's not. It's like you're just saying things to act like you know what you're talking about, so whoever's listening can. Oh well, he said yaw, and he said you just slightly do this, or like you're just saying words that don't give a direct answer. If you're
It
saying that
does.
there's no difference, wait, hold on. Let me just at least clarify this. Now, let's just say there was a difference, right, dynamically, in the way a pilot would have to handle himself flying over a spinning ball as opposed to a stationary Earth. There would be a big problem then in just training the pilot to treat the Earth as stationary and level if there was a difference, right?
If there was a difference where the controls would be different, yes, you'd be correct. But in
Yeah, there'd be a
effect,
big
hold on.
problem.
Can I please just answer the question?
Yep.
So no, there would be no difference conceptually in the model of either flat or round Earth for how a pilot would control a plane. It makes sense if you understand what I'm saying. I gave the
I want to make
analogies.
a point after he
I gave the
finishes.
analogies across the river. I gave analogies of a plane flying in the atmosphere, crosswinds. All you're doing is flying point to point. Whatever surface is doing beneath you or whatever the wind is doing, there's no difference. You don't know whether the ship is moving
Well,
or
but
the
then,
air is moving or the ship's
Stanek,
in.
why are you talking about having to like adjust like the 1.1 over a minute? Like all those adjustments wouldn't even be a thing if it was the same exact thing as flying over a stationary Earth.
Well,
That's
one
kind of our
second.
point. Yeah.
Yeah. Okay. So the crosswinds you're talking about, Zanuck, you said it'd be no different than adjusting for crosswinds. The thing about it is, bro, is crosswinds are a very temporary phenomenon. You encounter turbulence. You ever been in a plane? It's like, here, there's turbulence. Hold on, and then like 20 seconds later, 15 seconds later, it's gone. That is much different from having a literal constant crosswind the entire 6-hour flight. Because
you're making my point for me. So yeah, you have a crosswind. You notice, you know the path you're taking. You know checkpoints along the ground, and suddenly you have yourself kind of trimmed to the left with a little rudder trim to continue the course correction, and then suddenly you start getting off course, and you go back to a more neutral flying position where you don't have this crabbing or this yaw type of directional attitude with respect to the end destination. So yeah, that's what's easier to fly with respect to course than it would be to winds, because winds, like you said, are constantly changing. You could have a crosswind for part of your flight, a tailwind for another, and an opposite crosswind for the rest.
So you're saying Coriolis is like there's no factor at all to Coriolis in planes. Is that what you're saying?
It's like you said, it's a 1.5 mile per minute type of effect.
Yeah, but that all adds up.
That's
Dude. That adds up
walking
to 500 mile per hour difference by the time it adds up.
It adds up.
So then you're saying there is a difference between a stationary Earth and a rotating Earth.
It adds up. You're adding it up.
Yeah.
You're actually at.
Yeah. So that's the difference.
You don't gotta agree with me as
the
I'm talking.
difference between training a pilot to fly over a spinning globe as opposed to a stationary Earth. That's the difference you're talking about. But then you're saying there is no difference.
Yeah, you're saying that like when it's like, okay, when there's crazy riptides and all the lifeguards are out on high alert because they know that like riptides or more people are likely to drown. Exponentially, the rates of kids drowning go up exponentially. So all the lifeguards and all the beaches are on high alert when there's riptides and it's really huge swells and stuff. You're basically saying they're all crazy. There's nothing to worry about because they could just treat the ocean as if it's stagnant all the time. It doesn't really matter. That's literally what you're saying, bro.
It's
And
crazy
that's
double
nonsense.
talk every time you talk,
Yeah.
Zanuck. It's just crazy backwards, complete contradictions. But you say it with the confidence and use words like "yaw" and there's slightly banking and all these adjustments that you're talking about having to happen. But then none of that makes any difference because
It would be
stationary
continuous.
and do the same thing. Yeah,
The adjustments would be continuous. In other words, there's only one way to make a continuous adjustment that's static from the beginning to the end. It would be static because your crosswinds would be a different adjustment, but like the actual constant crosswind that we're talking about, based on flying at a constant velocity, it's called shooting a different azimuth angle to start with, and they don't do that.
And even if they were conscious of doing it and the pilot was like, okay, I'm on a spinning ball, I'm going to have to make sure that my eastward tangential velocity matches the Earth. When they slow down to land, they can't continue to accelerate with the Earth sideways. And that ends it. No matter what corrections that you could imagine that the pilot does, even though he's not trained to, it wouldn't work because you'd have to continually accelerate that 15 degrees an hour with the rotation of the Earth sideways as you're landing on a north facing runway south, right? So you can't. It wouldn't work. The planes aren't made to do that. They'd have to have jets on the side of the plane for it to work.
Exactly. It would have to have jets on the side of the plane and that's your whole argument, isn't it, Zanuck? That like you need a force to compensate for the fact that to counteract the fact that Earth is rotating. Well, like north-south meridian flights specifically, you would need sideways momentum to be gained, right? And that's like basically what you're saying is that it's automatically compensated for because pilots just know to lead their heading as if there's winds that they're a constant wind. That this is all it's all headcanon, bro. It's in your
No, that's
head.
really
exactly what
That's
you
not
do.
actually what's working.
I can't believe you actually believe it, Zanuck. You're smarter than
So,
this.
so suddenly you have been traveling southward, making a very, very tiny adjustment along the way, as we talked about, 1.5 miles an hour.
When you say along the way, you mean continuously the entire time.
Continuously, because you're trying to follow. If you didn't do this,
So
if you didn't hold on, if you didn't have a slight yaw, you'd find yourself off course to the west, and you don't do that.
Yeah.
What if you're going west? What if you're going west southwest?
Same thing. All would be a little.
How are you making eastward corrections?
If you're going west
southwest. Yeah, west southwest.
All you're doing is making a slight left type turn, a slight left
type turn. This kind of approximation language sounds pretty dangerous for people inside the plane.
A left yaw would allow you to gain
a left yaw.
Left yaw, yes.
Makes you go backwards.
Well, yeah, you're gonna basically trying to
make. Oh, it makes you go backwards. The pilot should be aware that they're going backwards when they do a left yaw.
Of course, if I'm traveling westward, southwest, and I have a left yaw, and I'm still pointing toward the destination, which is going to be Australia. Now, Australia is going to be way to the left of me, way to the east of me. If I just
you're just rambling, dude. Hold on. Get this, you guys.
Let me finish my thought here.
I want to go back to something
amazing.
You said before.
Unbelievable,
dude. You're just talking, dude. When you said before, and you admitted this, and you even offered this on your own, you said that the fact that the plane would be going west to begin with would make him lose his original eastward conserved momentum just by going west. He would lose momentum. His original momentum. It would slow down. He would have less tangential velocity just by going west.
You're going to race all your westward momentum. Yes.
Yeah. You're going to erase it all, but then you need 500 more by the time you get to the equator if you're going west southwest. So how's he going to lose 500 when he starts at 500 miles per hour eastward tangential conserved momentum? He loses it by traveling west, so he's losing the eastward tangential velocity he needs. And then somehow, just by slightly yawing left, somehow he's going to gain 1,000 by the time he gets to the equator backwards.
He knows the coordinates to travel a straight line to Australia, for example. Let's keep it over land.
What does knowing the coordinates have to do with it?
He could be going. Can you stop talking for a second? Because it's annoying to have you talk.
Yeah,
You're
because
making me
I'm
look bad.
pointing
And
out
I
the
don't want to look
contradiction.
bad. I don't want to look bad, so just don't do it. Just stop. You're flying
Okay,
from the,
well,
you're
I'm
flying
making you look bad. That's for
just
sure.
stop. Yeah, because you keep on you're making me get muted because I'm trying to get my point across, and I'm not
Oh, okay, go
yielding the
ahead.
floor to you interrupting me, and it's very uncomfortable to do this. So just stop as a
I'm sure
favor
that's
to
what's
me.
uncomfortable.
It is because you're obnoxious when you get like this. You're a nice
Well,
guy normally, but when you do this, irritating. Just stop talking. I mean,
I
let me have a little
appreciate
laugh.
your patience here, Zanuck.
Just
I
no,
really do.
it's gross. Just stop. Let me just get my sentence out, and you can talk after me. So I want to go over land. Let's say we go from New York to like down South America, Mexico, into South America, down to Chile. We're going to go southwest, like you're talking. We know the straight line path by the coordinates along the way. We make sure we stay along that path, and we'll notice that we're going to slightly be giving a westward yaw to the plane along the way. And yes, over 24 hours, or however long that flight would take, something like 20 hours, we would then, all of our tangential velocity in the northern hemisphere would be negated and turn to the other direction to go 1,000 miles an hour or 500 miles an hour eventually to the southern tip of South America. Now, if we ended up at the equator, that we would just kill all of our westward tangential velocity, kill all of that, plus gain another 1,000 miles an hour to land the equator. That would be something you could calculate as well. And
You're just stating it. You're just like saying it as if it works, but you're not giving any mechanism. And you're saying
you turn
westward
the
instead of
plane.
eastward.
I've said it for years.
You're talking about going west would make them lose their original eastward tangential velocity. Now it only goes west and southwest, so it has no way of like gaining more eastward when it already lost its eastward tangential velocity from going west southwest. So there's no way it could somehow then gain 1,000 by the time it gets to the equator backwards faster than it's going forwards.
If you're flying on a jet, you're able to look at the heading, I mean the heads-up display, and where the dot, which is the direction of travel, where it's pointed, and you'll see it's not pointed directly at destination. If you have maps out and things, where it should be with you, and you have landmarks and things, mountains, things, structures in Mexico. You're trying to go equator. You'll notice that it is skewed to the left. The skewing to the left is an acceleration to the east, and that acceleration will add up to be negating your westward momentum as you left the airport in Chicago, and it will be adding so much so that you will actually equal the velocity, the tangential velocity of the equator's final destination.
How? How? From what mechanism?
By having the plane yaw slightly to
the left. You mean south?
south, to the west, to the east. You'd be pointing it a little bit to
No,
the
no,
east.
no. It's going west. It can't go
I
east
know
and
it's
west at the
going
same
south.
time.
It's going southwest, right?
No, I said west southwest. More towards the west.
West southwest. Fine, mostly west. You're leaving New York, you're going to the equator. If you notice that the path we're going to take, we can draw a straight line to this equatorial. We're going to Ecuador, which is near the equator. We have a city that we're going to land in, and we have a straight line to it. If you notice the heading on your heads-up display, dot will not be in the direction where you are on the map to where Ecuador is on the map. It'll be slightly to the east. Even though you're flying southward, the rate of which you'll be going eastward will be so great that it will negate all your westward momentum and give you eastward momentum by the time you get there.
How?
Very, by having a 1.5 miles per hour per minute deviation from your direction along this path.
Yeah, but you're headed in the opposite direction, so it doesn't
This
work.
is the answer. I've given you the answer.
Let's calculate what the angle would have to be. Let's calculate what the constant offset angle would have to be to see
Good. Now
how
we're
much of a
thinking.
difference.
Good for you.
There you go.
To see how much of a difference there would be. So if we made a triangle, I did a simple. This is going to be a very simplistic approximation. Okay, no, it's not going to be exact. We can get more exact if you want to do more harder math. But I just took the 550 miles an hour times 8 hours. That's 4,400 miles. Okay. And then I took the beginning speed at every hour, starting up at the Alaska latitude, and going all the way down, 4,400 miles south. So I said, 200 miles, 300 miles an hour, 400 miles, 500 miles an hour, 6, 7, 8, 900 miles an hour. So, and then I added those all up, divided by 8. You end up getting like a little over 500 miles deviation. It's like 550. Okay, so 550 miles deviation, right? That would be your horizontal deviation from west
It
to
doesn't really
east.
matter too much. But are you talking? If we're going to be at 45 latitude, we're going to go to 0. You know how the distance, right? All you can do is take 45 times 60. It'd be
Who said it's 45? I'm talking about in terms of distance traveled. I mean, like
2,700 miles. We know because I know the latitude of New York. We're at 45 degrees, right? Upstate New York. So we fly from there to the equator. We know that we can southwest, like he said, 2,700 miles as a crow flies.
2,700 miles. Okay, what's the ground speed change?
Just to the equator, but we're not going to the equator. We're going southwest. It's going to be farther. Now it's going to be a triangle. Now we have to figure the angle of which the equator destination, Ecuador, is from the longitude of New York. And let's say it's another 20 or 30 degrees. You can take the 20 or 30 degrees and multiply that in a trig calculation and get the distance is more like 3,000 miles. So did you say 3,000 miles or more? Did you say 5,000?
I was saying an 8-hour flight, but let's just fly to the equator, right? So
I think it's 3,000 miles to the yes.
Okay.
With an angle, with a southwest trajectory.
Okay, so just real quick, in case you didn't hear him say that,
6 hours.
you would lose your eastward momentum that you had originally. Like say you took off from a 500 mile per hour eastward
no.
tangential.
I'm not
You
even
would
worried
lose
about
that. So you have to go to the point where he loses all his eastward tangential velocity and then starts to gain all of the 1,000 that he needs by the time he gets to the equator west southwest.
Well, I got you. We're gonna make it more simplistic than that, though. Like we're literally just gonna shoot a triangle. Okay, we're gonna draw a triangle on the map, and we're gonna say, okay, this is how much the ground speed changes on the rotation of the Earth from here to the equator. At the equator, it's 1,040. From up here, it's like what? What is it gonna be at New York? Like 400?
That's 45 degrees, so it's halfway. I think halfway
Like
is
700.
well. If halfway, if it's 90 and half is 45, it should be.
So it should be 500 miles an hour difference.
Close. It's not exactly 500. I think it's
520.
Yeah, it's around 5. Yeah, let's say 5.
say 5.
Yeah, so 500 miles an hour and at 3,000 in a 6-hour flight. Okay, so let's just make it real easy. Let's take 500 divided by 6. 83 miles an hour, or 83 miles difference change. Okay, so basically every hour we're gonna change like 80 something miles an hour for 6 hours. So you could say if you did not alter your heading, if you just flew straight south and made absolutely no correction, you made a dead reckoning pure south, okay, and flew into it, you would drift by about 500 miles, okay.
Yep.
So now we take a tangent angle, okay. The opposite will be 500 and the adjacent will be 3,000. So opposite over adjacent is 500 over 3,000. It's 1/6. Okay. So let's see. Okay. So the inverse tangent of 1/6, because tangent of the angle would be 1/6, but we're solving for the angle, so it'd be inverse tangent. Inverse tangent of 1/6 is 9.46 degrees.
Yep, 9.46, 2, 3, 2, 2, 2, 2, 2.
Yeah. So you got a 9.5 degree offset from south. So what you're saying by saying that they take this flight, this is not account. We'll negate all crosswinds because those are temporary and they adjust for those mid-flight for a few seconds and then they're back onto the same path. So in calm conditions on a clear day, right? You've got a 9.5 degree azimuth angle offset you have to shoot from the time that you take off. So you're never actually aiming at where you're going. You're offsetting by 9.5 degrees. And this is remember, this is going to be different depending on how far you fly, where you're going, what the compass direction you're flying in is. Are you suggesting that pilots always look at some kind of declination angle chart when they take off from where they're going to
No,
account for this?
they're flying point to point, and you're also forgetting the effect of air mass. Remember, the air mass is also accelerating as you travel through it southward, and you can think of the plane in the air. What is the force of a 1.5 or 2 mile an hour delta every mile, every minute on the airplane? It's not very much. It's not going to be in sync. It's going to have drag across the surface of the plane, and actually is acting on the plane like a sail from the side.
Wait,
That will
no,
also
you're
be
saying
that.
a sail is pushed by wind. Now you're saying the air mass is moving the plane without it being a wind?
Yes,
How?
its
What's
tangential
the
velocity is
mechanism?
going. You can't even let me answer it, can you? The tangential velocity of the air mass is still, and we're not talking about crosswinds, the path will increase as you go south to a factor of 1.5 miles per minute. So it is a force.
So you're just
not a
saying
one.
it's just going to match the offset angle.
Well, no. If it was fluid, if it was a river, you wouldn't have to worry about it because you'd fly in the river and you'd get there. You just point straight, and the air mass would take you with very little drag,
Oh my gosh.
very little drag to the Central
Yeah,
America.
it's like
Hold on,
what you're saying is
let me
ridiculous,
just
man.
goddamn finish a thought, please, come on. But in air doesn't work like water, so yeah, it's much less of a factor, but still is a major factor over a 8-hour trip
Bro,
or a 6-hour trip.
you just said if it was you just said if it was water, it would just carry you and you wouldn't have to worry about it.
Exactly. If it's water,
But if it's air,
you'd
then
be in
you
the
would have to
fluid,
worry about it. But the pilots don't have to worry about it. But they do have to worry about it. But they
just
just are
like when
trained
you're
and
in a
treated as
boat.
stationary. But they don't have to worry about it. Oh, but they
Just
do have to worry about it. But they don't. You're
you
just
understand? If I have a
contradicting yourself.
boat,
I didn't
and
realize
What
it
you're
was going to
saying
be
is
that much,
laughable.
dude. I didn't
you're not
realize
going
it
to
was going to be
understand.
9.5 degrees. That's a lot, dude. That's like a
Yeah,
whole lot, dude.
yeah. And the air mass isn't
Dude,
automatically correcting that, Zanuck. That's just hopeful thinking.
yeah, it's almost like everything's always automatic the way it's accounted for with the way like planes fly and refraction works on curvature
Yeah,
and stuff.
because it's just like there's no way for them to explain it, so they just have to say things
It's automatic.
as if it's automatic, and it just explains it. But then they have to kind of like add some like real sounding words to it to make it like act like it. Oh, it just works. It just works. You don't have to worry about it. It's just it's not dangerous at all to have it be slightly this or slightly that, or I mean, all these approximation things that the words you're using. There would never be any of that. If you're flying a plane, it would be exact. They would know exactly what they're doing. And if they would land safely because they treat it as stationary. And the only way they could treat it as stationary and land safely is if it's actually stationary. It's
Because
that simple.
the question would be perspective. It would be like because you're going to fly. I mean, the only time you're not flying at a relatively constant speed in a plane is takeoff and landing, right? Which is a very tiny portion of the flight. So the rest of the flight, you're flying at 550 miles an hour, and you're not deviating from it. That's your speed, and you're keeping it the whole time, right? So because it's a constant speed, it's a constant angle. That's just shooting a different line. If it in fact wasn't that, if you were making corrections, the way the corrections would look, it's like, all right, I'm aiming straight south. Now I'm off. Now I'm going to turn this way. Now I'm off again. Now I'm going to turn this way again. Like they're definitely not doing that. No one's going to ever try to say they're doing that because that would be ridiculous, right? Like that's not what
Yeah. And
pilots do.
even if they were
So
doing that, like even if they
They're
were
constantly
conscious of
doing
it,
that. What are
it
you talking
still
about?
wouldn't, even if they were conscious of doing it, which they would have to be if they were actually trying to keep up with the spin of the earth, even if they were trying to keep up with the spin of the earth and they knew it was spinning and they weren't just trained to treat it as stationary, they wouldn't be able to continue accelerating with the sideways speed of the earth
right.
as they're slowing down to land southward.
It's almost as if like they train on this like flat stationary model and they wouldn't notice when they switch to the real model in real life that's actually rotating. They wouldn't notice that they're deviating 9.5 degrees.
Yeah, right. Exactly. They wouldn't have to worry about it because somehow it works still.
Yeah.
It's laughable,
All right.
Zanuck. Just laughable.
Well, I gotta get off here. It's super
Hey, thanks
super
for
late.
your input, man. It's awesome that you could show the math and maybe put it in a context that just is unarguable. 9.5 degrees, that's a lot. It's not just like, oh, well, you just go slightly left and it makes a difference. Come on.
If there was no wind and if you ignored the wind, he'd be right. You'd have to take off and plane at a 9.5 degree, close to 9 degrees or so, yaw, and fly southward, and that would make up for the rotation.
Yeah, but he would be trained to do that. He wouldn't be trained to do that if he was treated as stationary.
Fucking A, dude. Dude, every
Yeah.
time you do this, you can't let me finish a fucking sentence. I say this every time you talk.
It's trying to
Go
say
ahead,
sit
man.
inland.
I listen
whatever.
and you just keep on talking. So I stop, and when it's time for me to talk, just let me have
Is a 9.5 degree yaw something that they would have to be cognizant of, man?
No, nothing.
They would not be cognizant of a 9.5 degree.
No, you wouldn't know it. All you're doing is trying to keep. God, just plane time. Just the plane being out of balance can be a 3 or 4 degree change in how it's going through the air relative to positions on the ground. You're constantly using rudder. You're constantly using dipping the wing. You're trying to keep the thing on course. That's why you have controls. If you didn't need controls,
now you're comparing it to
fucking
things
A, dude. Stop it.
Dude, but wait a minute. You can't just. I'm not going to let you just continue
babbling
babbling when you.
Goddamn sentence. Stop it.
Okay, yeah, but you're just going on as if it makes sense, but it doesn't, because you're saying there's constantly, if he was off balance, he might be this far off, but he would be aware that he's that far off. But you're talking about him not even being aware of it and it being corrected all of a sudden without him having to correct it consciously. And that doesn't make any sense.
Well, what he's saying, I know what he's trying to say. And let me just like reiterate to you guys what he's trying to say. Because what he's trying to say is that basically there's always going to be making minute adjustments as little tiny stuff happens, little pockets of air, little crosswinds, little stuff happens. They'll make little adjustments. Yeah, I mean they'll become aware of it when it happens, right? Like,
yeah,
but
exactly.
And so he's like equating that to the same thing as this 9.5 degree continual from beginning to end of flight adjustment
that they aren't aware of.
Well, they're not comparable because the magnitude is so much larger. But even if they were, like, that's not how it actually. Like, the problem is like no matter how much you rationalize this as making sense in your head, even though it doesn't. But if you just alter the magnitudes of it as to something minute, so it does make sense, that's still not what they actually do in real life. Go talk to pilots. Look at the interview. Look at training manuals. Look at flight simulators, because the flight simulators that you use. Like, they actually train you how to fly real planes, and there's nothing ever in that about accounting for X many degree offset for the tangential change in the speed of the Earth.
Yeah, and they would overtrain their pilots. I mean, they always come up with like, oh, they don't have to worry about it, or it wouldn't even be such a big difference. They would have to train the pilots. No, they would overtrain their pilots to every single possible little minute scenario that they might run into. And if they don't include the Coriolis or any of these kinds of adjustments, that means the only way it could possibly be that they're trained that way is because it actually is that way.
Like, a person can make the argument maybe is like, oh yeah, it's off by like a 1/4 degree. Like, maybe a person wouldn't notice that because it's just like they're following their flight computer and they're in a path, right? But like when you have this spinning dial compass degree readout, bro, if I'm supposed to be aiming at 90 degrees south, or it would be, let's see, 180 degrees south, and I'm aiming at 190 instead, that is a huge.
But that's not what you do. So you were wrong about. I should have jumped in early, but I was. Listen very carefully. You're not, even though that you did the calculation with simple inverse tangent for 9 degrees. It's not 9 degrees because when you're flying, you're using your gain 1.5 miles per hour per minute acceleration to the east, and that doesn't require more than a 1 degree yaw in your airplane. It's just a little bit of a side, like it's like a little bit of a crosswind. So the end result will be 10 degrees, but you don't need to do 10 degrees dead reckoning.
Well, how does the pilot do it without being aware that he's doing it?
Bro, we just did the math on it based on the speed.
Wrong. That's incorrect.
Well, if you don't do it as a continuous function, then that means it has to be sometimes less and sometimes a lot more.
No, it's not. It adds up. It's called an acceleration.
If you don't do it as a proper true average, because I calculate it as an average, the average is going to be the smoothest curve you have. If you don't do it as an average, that means you're going to have numbers less than that and numbers more than that. So there's going to be times you're not correcting 9 degrees, you're only correcting 4.5. And then there's going to be times you're correcting 13.5. And then like saying like that they wouldn't notice that, like that's even more noticeable. Like me giving you the smooth curve.
It's acceleration. Getting one. It's acceleration. It doesn't.
What does that mean? What does this one-liner mean?
It means if I want to accelerate to that speed, I have to a little bit of yaw into the plane, and I can accelerate to 1,000 miles an hour.
In order for me to accelerate, why would I need to turn left?
Jesus is Lord. the love of Jesus is Lord, all is holy. Just stop. All you have to do is accelerate this body flying through the air to 1,000 miles an hour plus whatever, let's say 1,000 miles an hour over 6 hours, and it's not that much. And that all that takes is a left deviation to the east to be able to create that acceleration.
But
You're
the
trying to do
point,
it mathematically.
the original
Not a
point, Zach,
triangle.
is
Okay, forget
he
about
can't
it.
accelerate up
I
to 1,000 miles an hour eastward if he's only going west southwest. There's no way to accelerate the plane backwards, bro.
No, I mean, he's what he's saying is a little bit. We calculated a little bit, and it ended up being an average of 9.5 degrees. I mean, that's what the little bit he. I mean, he's just using words to colloquialize it into seemingly believable, minute terms. But that's why we did the math, because that's what it comes out to be on the triangle is 9.5 degrees. And yes, if you start at the origin point, it is a continual 9.5 degrees. It's not like I just shift it, just pull a little left. Like that's what when you're saying pull a little left, what you're saying is 9.5 degrees left. That's what you're saying. I'm just filling in the gap with the
think
the math.
about it. Even if he was doing that to pull a little left or whatever, like it would change the flight path. Like we see like a flight from Dallas to New York to Dallas, it goes straight to Dallas. Well, Dallas is in the globe paradigm. They have to admit Dallas is moving independently of the plane's movement, so it would be coming towards the plane. And if you were doing that adjustment, even if they were trained to do it, they would go southward and meet the city where it's going to be, not where it was when it started off, right? That adjustment would, yeah.
That's the crux of the issue right there, is that you would have to constantly be updating your path. You would constantly be having to update your flight route depending on where you are in that moment in time, instead of just calculating it based on where you're departing to where you're going to arrive. Every flight path is calculated by where they're departing and where they're going to arrive. And yeah, you're right that they do account for like things like winds here and there. But but to claim that they're constantly updating their flight route based on the moving arrival spot, that's nonsense. That's not reality. That's just what you're saying.
And to top it off, even if they could do that, or they did do that, and the flight path was southward towards Dallas, a little bit west, but mostly south to meet Dallas by the time the 4-hour flight, or it would actually be a lot shorter flight. But regardless of that, even if they got to Dallas and Dallas is continually moving eastward, then they would still have to accelerate the plane eastward to be in sync with Dallas when they're landing on a runway that could be, they have to go around the airport and then aim in like a north south or north southwest direction or north east direction or whatever the angle is of
It'd be different for every airport. Yeah.
Does anybody know what a constant rate of change looks like on a graph? It's a line. So that's what you would be drawing on your map is a line. It
just doesn't work. There's no way.
It's like if I need to get my
tires aligned, and my car's pulling to the left a little bit, like I'm gonna notice that. I mean, even if it's just so ever so slight, like I'm gonna notice that there's
if it's only 9 degrees. Yeah,
you wanna go that route. Hold on. Constant change, be a line, an angle, but acceleration is a squared function in it. That's why we call velocity the first derivative of distance with respect to time, and acceleration is the second derivative of distance with respect to time. Completely different. I'm talking acceleration, and you're talking the line.
No, I'm talking about from a practical point of view of having to just correct my car over and over and over again. Even if I have to correct my car all the time, if I have to do it 9 degrees more one direction as I'm going somewhere, I'm going to notice that.
You're right about acceleration being second order, but the thing is that acceleration, we accounted for that in the original math that we did. We calculated what the rate of acceleration would be in order to create that amount of a velocity change in that amount of time.
That doesn't equal the angle. It will not equal the angle. You're forgetting about a squared function. You left it out.
Oh,
do it again. You're incorrect. I'm just telling you.
So what would the correction have to be, Zanuck, that they're not aware of that somehow works?
It's going to be a progressive.
Okay, so the pilot is making sure to do this, even though he's not trained to.
No different than if you had a crosswind. A little different, but not.
Hold on. Is your rate of change? Is there going to be hold on. Is your rate of change of acceleration increasing or is it constant?
Not constant.
Your rate of change of acceleration. I thought
acceleration is constant.
Did it?
Acceleration is constant.
Yeah.
Not the
So
rate
if
of change. One's velocity, one's acceleration. Second derivative of distance with respect to time.
yeah, your
You're
acceleration.
talking about only the velocity. You're giving me only velocity.
He's just Zanuck. You're just gish galloping, bro.
I'm not getting. No, I'm being very accurate. There's a change of velocity. Changing the velocity is an acceleration. He's saying the velocity is staying constant. You're getting a change of velocity, which is an acceleration.
The plane's velocity is constant, but we're talking about in relative to the ground. Relative to the ground, the acceleration that you're encountering between the start point and the end point, we can calculate. You're saying it's like 1.5 or whatever. We know that we're traveling 3,000 miles, and that the velocity of the ground speed is going to change in between that time. We said 600 mile an hour, and so 600 mile an hour. And the plane is going to take, what was it? It was like 6 hours to get there. With a little leftover math, I think it came out to like 83 miles per hour change per hour. So if you make a constant acceleration curve and you're changing each hour 83 point whatever, yeah, it's like 1 point something miles per hour. Well, I guess it would. I'm used to doing meters per second, squared in terms of acceleration, but that would be the continual increase throughout every, moment. It's like 1.2, 1.3, whatever it is.
And that would change the flight path. That would change the look of the flight path. It couldn't just fly straight there, right?
Yeah. So like, if the acceleration is increasing at a constant rate and you're not making it parabolic, like you're not making it just go
You're talking gibberish again. If you change acceleration is not constant, then that's called jerk. So that's a third derivative of distance. So what are you talking about? We got velocity, first derivative, acceleration, second derivative, jerk, third derivative, snap, crackle, and pop, the rest of the derivatives. But you know how it goes.
Zanuck, what do you say about the flight path? How do they fly straight from New York to Dallas in one straight path if they're having to adjust for this eastward tangential velocity?
Did you just say? No, he just said acceleration it wouldn't be constant. Like, what are you saying that constant accelerations don't exist, bro? Like, what are you saying?
No, I said it is you said the acceleration is changing.
No, dude, the velocity is changing. The acceleration. We're dividing out the math to make it to where we can calculate the acceleration as constant, so that the math becomes easy.
You said the acceleration was changing. I said no. We're talking about the velocity changing, which is
okay. If I said that, I'm sorry. The velocity is changing. We are maintaining a constant acceleration. When we're talking about changing, well, by the way, we're talking about relative to the ground. Like the actual airspeed of this plane is 550 miles an hour. It's not changing. We're just talking about the velocity of the plane in relation to the ground.
You have a velocity.
Tangential. We're talking about the tangential velocity along the ground.
So that's changing too. That's changing by an acceleration.
Yeah, that's what's changing, and the force the force that's changing it is this accelerative. It's not a force; it'd be an acceleration, but I mean, like the force off the engine. I mean, the force off the engine, sure, whatever, which is causing acceleration. Either way,
not either way. That's what's causing the acceleration. If you put the plane in a yaw and you're not in a crosswind, just use rudder only. We could dip a wing too, by the way. Put it in a yaw.
You could dip a wing. No way. Dip a wing.
Why do you do this? Every single time I talk.
But I know you could, bro. Like, I know that's what it would look like. Like, this is where I'm agreeing with you. If you were to make these corrections to account for these things, that is what it would look like. My whole point to you is that is not what we see. We do not see pilots tilting their aircraft wings. I'm thinking over here, thinking Ospreys, bro. Sorry, Marine Corps. We're not seeing them tilting their plane. That little cat in that plane is not tilting his rotors 9.5 degrees to the left and flying constantly at that angle the entire time. That would be absurd.
You mean tilting his rotors? What do you mean?
His wings, tilting his wings. I said
No,
not
no,
rotors. I meant
you can change directions two ways. You can dip a wing and pull back in the elevator, or you can just give you a rudder, and that's called the yaw. The yaw rate is what we're talking about. If you have a yaw, you can accelerate the plane to the east over 6 hours to achieve 1,000 miles an hour net change in velocity tangentially. If you don't agree with me, go do the calculations again. We have an acceleration. It doesn't take very much of a force to do. It's different than a.
Hey, what do you mean? Don't agree with you about the way a plane works? It's not about how the plane works. He just said the flight paths do not reflect these kind of adjustments. They're never doing that.
And they shouldn't.
Well, they should. If there was adjustments to make, then
No.
the adjustments would be apparent in the flight
No,
path.
you're confusing the flight path with the control inputs.
let me.
What?
You're confusing the flight path with the orientation of the plane and the flight path.
Not confusing anything, dude. You're trying to confuse everybody.
The direction, dude. You keep on doing this, and you're saying gobbledygook.
Here, let me just
flying directly from point A to point B, and along its path, the plane might not exactly be. Fuselage might be not pointed. The direction of travel would be that straight line, but the orientation could be slightly yawed 1 or 2 degrees without you really
All
noticing.
right, you're making the man break out a whiteboard here to show you how wrong you are, Zenik.
All right, look.
Have you?
Not to scale. This is going to be not to scale. Okay, this is going to be not to scale, but I'm going to draw this. Okay, so this black line here, I'm going to draw another red circle. This is origin point. This is origin point, okay? This is destination point down here, okay? This, I'm just going to draw this in blue. This angle is going to be like 9.4 degrees. That's going to be a 9.4 degree angle. Now, we all already established the triangle. You could create a constant bearing from the beginning to the end, and it would basically this whole line. Here I'll draw it so we can see it. I'll do the transform. This line right here, as you flew, this line would shift to the left. So you're flying at this angle, but the wind is pushing you the whole time. That's why you offset it. So by the time that you arrive there, this bottom tip here ends up in the circle. That's one way to do it. What he's suggesting is that, I'm going to draw this one in yellow, and this is going to be kind of bad. He's suggesting you just fly straight there, and you're starting to make small adjustments the whole time, right? But the thing is all this is getting pushed off. You're having to trail off the entire time. So it's like not constant. It's all over the place. Or if you never make a negative adjustment, you never go off in the wrong direction. Let's say you only go straight or to the left. You only go either straight or to the left, so you don't make opposite direction adjustments. And you were to go straight the whole time and just make some crazy adjustment at the end. I mean, do you think an adjustment of this is not going to be noticeable? Like the straight line is the least noticeable thing that you're going to do. Because if you don't do the straight line, that means at some point you're going to have to make some huge over adjustment in order to account for it, make it up. Now, I'm drawing this inside the triangle. What it would actually look like is I should start like out here. Oops. Because you would actually be getting pushed this way, and you're having to adjust and end up over here. So because the wind is going, or sorry, not the wind, but the earth, is rotating away from you in that direction. So you're having to bear like this in order to account for that. So every line I draw on here is getting pushed here to the left. If you took off up here, the reason that you have this offset distance at the bottom is to account for the rotation of the earth. That is a fixed distance. This is the distance that we calculated. It's like 500 and whatever miles it was. It's a rough approximation. It's not exact, but it works for the purpose of this illustration. You cannot say that if you were under these conditions and you had to make all these corrections to get there, that you wouldn't notice any. Like, do you understand how sharp of a bearing change this is from here to
You're
here.
talking yourself into a tizzy. Let me respond. I understand all of it. I fly. I mean, other stuff. It's not a big deal. You made an assumption, a dangerous assumption to start with. That this 9.4 degrees has to be accommodated only by a yaw angle, kept constant. No other factors acting on you along the way. I already got done telling you that the air itself will push you along too and make that point. But let's say there wasn't, a need for that. You say you had to fly. You had to make that angle. Let's say there was a crosswind the entire time. You still can have an acceleration, like planes when they take off. You can do this. Make this graph vertically. Do I have to have a 10-degree angle of attack upward to get to 30,000 feet in a certain amount of time, or will the plane have enough lift that it lifts you up even with a lesser angle of attack? That means I can sometimes fly level and just increase speed, and the plane will fly upward without even making the nose go up. So there's certain configurations of the plane that can make it accelerate up or make it accelerate left or right, where it's not, you don't have this great, tremendous yaw of the plane. You just have a
But
force
there's going
acting
to
on
be
it.
a yaw.
The yaw is what I'm saying. It's just the nose is not exactly pointed to the destination. Now, you made a bunch of errors in this simulation of we're pointing the plane to that circle, that yellow circle at the bottom, but it is moving to the east over time. And all we have to do is make sure we follow and stay on track based on the things that are beneath us. And those are small little adjustments along to increase an acceleration, a net acceleration along the way of 1,000 miles an hour over 6 hours, of around a mile to 2 miles an hour per minute.
You keep trying to downplay it by saying small amount of just small adjustments, just small. He's showing you he pulled out a whiteboard for Christ's sakes to show you that these aren't just small adjustments that are negligible. You keep trying to downplay it, bro.
I'm not. I'm trying to give him a little. He's quiet because now think.
I was waiting for you. I was letting you talk. Actually, I was trying not to interrupt you.
But think about doing this. Now take that 9.4 degree just takeoff point where you departed, and think about making this. Now we know the change in tangent somewhat linear, not really, but it's somewhat. Pick a spot like below. We started with New York, we're going to equator. Think about just going to Florida, or like Louisiana from New York, and think about that 9.4 degrees. Where does that put you? And that might be the answer that you're looking for, because that 9.4 angle would not put you in that path that you want. Let's say you had to fly over Louisiana to get to the equator, and if you did a 10-degree yaw, taken off from New York, you would be, by the time you got to Louisiana, you'd be well off course. So it's not going to be linear. That's the point I was trying to make.
Louisiana is not directly south of New York.
We don't want it to be south. We want it to be southwest. But if you want to use the south one, it's easier. Let's say we're taking off from Winnipeg and we're going to Dallas, so we're directly in line. What happens if you? Where would you be if you had a 9.4 degree yaw and actually went angle deviation? Would that match the tangential velocities?
Oh, you're asking me to do more math, and I pull out a map to do all that.
I'm trying to help you show you how an acceleration changes everything, and you're still making it linear, and you're not getting past the thing. I'm just pointing it this way. The change of this yaw angle will create an acceleration. The acceleration will not be a linear relationship as you drew. That's the point I'm trying to make.
Which is why I drew it in yellow as a curve, to show you that if you did it as a curve, your correction at some point would be massively noticeable.
No, you're not making a correction because you're accelerating, building on yourself. That's how accelerations work. You're not going to have that. That's why that last one was
okay. So let me ask you this: what shape? Do you want the shape to be a curve or a line? Because there's only two choices here.
It can be a straight line.
Okay, if it's a straight line, it's this line right here. What other line do you want?
Correct. And your net gain, your net result was a 9-point deviation from the original heading. But you're not flying that with the direction of the. You have an acceleration that you lesser because you're accelerating the plane.
So
You're
you
applying a
just
force.
admitted that it's not going to look like the curve. It's going to look like the straight line. Do you understand that what we're drawing here is flight paths, and
Yes, but you
that
have an
the math that we did is what is accounting for the drift that you're encountering mid-flight? Like that you're trying to account for the drift a second time and saying that's why it's negligible. It's already been incorporated into this math.
Okay, let me put it to you different. If I was to shoot a missile now, this is ballistics. I would point it 9.4 degrees and shoot. You'd be right. You'd be right. Now,
Yes.
if I fly now, if I have a rudder and I'm able to apply a force, that means I'm applying the entire time. If I apply, this is where you're going to, the light will go on right here. If I apply a force the entire time, that means I have an acceleration, which I didn't have the acceleration with the missile. The missile I pointed, I don't have an acceleration. I'm just going to fly it, and it's free fall from the point I depart and land. With the airplane, I'm applying a force. The force is creating acceleration. So I don't need the angle of attack that the missile had because I'm accelerating it with force. You see the difference?
Bro, the force that you're using is
You don't
keeping
see it,
the
do you?
plane in the air. I do
No,
see it. A
no,
better
wrong
illustration
quote.
would have been a bullet. If I fire
No.
a rifle out of a gun on a gun range and I've got a crosswind that's constant between me and the target, I need to put a hold like 6 inches to the left over here at 500 yards for this weak wind. I'm using a real world example of something that, like I do, right? So, like if I'm shooting a 500-yard target with a 4x scope and I'm accounting for the tick lines on it, I got it all centered out, zeroed out. I don't hold center mass because I know that I've got this crosswind coming. I'm going to hold to the left side of the target, so I end up by the time I hit the target to the right. And what that's going to look like, simplified, is this bullet is traveling straight, but the wind is pushing it to the right. So, do you remember that thing that I drew that was like this? This is what the bullet's doing. It ends up looking like a diagonal line because the bullet's actually traveling straight just like this line, but when you add in the crosswind and you do the sum of the vectors, it ends up looking like this. Because what do you see? Like, let's zoom in. Let's zoom in. Do you see all these little tick marks? Make this like your infinite number of approximations between an infinite number of points in between the start and the finish. That's what it's looking like on like a super, high FPS camera. But otherwise, it's just a line, bro. I mean,
missing the point entirely.
you're just like throwing out this.
No, listen,
the planes
stop.
have lift,
Can
and
I
that lift
respond?
is a force, and the force is an acceleration, and that accounts for it. Like you're just.
Can I just give me a sentence?
Can I please just talk forever, guys? Please.
No, I haven't said anything. He's going on and on with this drawing. I appreciate your whiteboard. That's actually cool, but you're forgetting. I gave you the analogy, and you piled on with a non sequitur analogy. The analogy is this: if you're ballistics, you're right. Shooting the thing from that departure point and accounting for this 6-hour flight, want to land at Ecuador. Yes, you would go 9.4 degrees and shoot it target. Now, if you're going to be flying and applying a force the entire way, that's an acceleration. You won't need that yaw the entire way. You won't need to be pointed that way.
Let me ask you this. Let me ask you about this acceleration. This might make it easier. Okay. What is the purpose of this acceleration that you're applying with the engines of this plane? What is it counteracting? Gravity, right?
No.
No. Oh, wait.
No.
Because if I got the plane flying directly south, just say it's really high in the air, and it's flying 550 miles an hour to the south. If I cut the engines off completely, it's still going to be flying 550 miles an hour to the south. It's just going to start falling, right? It'll even be drifting to the left because the crosswinds are still going to affect it. The whole point
will it be accelerating downward?
Yeah.
Yeah. Okay. So good.
So that's what I said. The whole point of the engines is to offset the gravitational acceleration.
No. So you got another vector you're not taking in consideration again. Missing all these simple terms. Come on.
The only other vector that would exist would be as if you added an angle to the wings, which would then create friction with the air, which would push it off to one side or the other, which would add an extra.
That's not either. Which let me tell you, it'll be easier. I'm not gonna. I can make it turn two ways. Like I told you, I can bank the wings, pull back in the elevator. That'll make it turn, or I can just crab. And I'm crabbing, and I'm adding power. That power will allow us to accelerate like I'm taking off, but I'm constantly taking off, but going left rather than up and down. The power is doing two things. It's got a vector down and up, and we have a vector now to the left that is actually
because you angled the wing.
The tail section is now been angled.
Okay, whatever. You angled part of the body of the plane.
Let me finish, and you'll get it. Why you're trying to second guess me, and you're wrong. I angle the airplane, the entire fuselage, propeller. Now the thrust vector is not going straight anymore down to that red yellow circle. It's going to be slightly toward the destination, 4 degrees, but not exactly, because I'm accelerating the entire time. So I don't need to have the just like when I'm taking off. I could be totally wings level, attitude 0, no angle of attack at all, and the plane will still rise up in the air due to lift. And as long as I get a positive lift, I have an acceleration. And if I have acceleration, I can continue to go up into the atmosphere. But I'm fighting against gravity with a positive have an acceleration, because negative acceleration of 9.8. If I was only matching 9.8 per second squared, I'd be flying. I would not be gaining altitude. Gaining altitude, I'm actually accelerating, because
just one second. Okay, so you're saying you're going to accelerate until you reach the necessary velocity in the total velocity vector to be heading in this diagonal direction, then you're going to just leave it even keeled the rest of the time?
Nope, I'm going to continue to accelerate the entire time, because that's what acceleration is. It's a change of velocity. The entire time I'm in changing velocity. I don't need a 9.4.
So you're increasing velocity. You're starting at 0, and then you're smooth curving it all the way till whatever it needs to be here, right?
I'm going straight. But what's curving is with respect
so
to
I know. Let me see if I can find a video. Well, I'm not going to be able to find a video. I wish I had a flight simulator I could show you. What that would look like is your plane is pointed to the south, and you're flying to the south, but you're actually like moving in a diagonal line. So everybody in the plane is going to see this super weird effect. They're like pointing south, but they look at the ground and they're heading in a diagonal angle along the ground.
No, it's not that dramatic. That's what I'm saying. It's not that dramatic at all. You're only trying to get. Look, you know what a plane. If I put a plane on a still day in a 10-degree yaw and leave it there, I will accelerate to the direction I'm yawed, and I can match a 20-mile-an-hour crosswind and keep it constant there if the wind is still there. But if there's no wind, it'll continue to accelerate. So we're saying
and you're going to gain more and more and more diagonal velocity while keeping your. Yeah, that's what I'm saying. And you're saying it wouldn't be noticeable,
right?
Like your plane you're basically saying I have a level plane, but it's flying at a diagonal angle, and that angle is getting sharper and sharper and sharper the further I go, and saying it would never become noticeable.
No, your tangential velocity is being matched.
By what?
Why it's confusing.
What's it being matched by?
1.5 miles per hour per minute. It's not noticeable. Even though your net tangential velocity is increasing, you're not going to notice, because the ground is only seeing a 1.5 miles per hour per minute type of change. That's why you're missing it. I feel like I'm going to go.
I just don't know why you say planes fly sideways.
You have to have a little bit of easterly direction to increase your tangential velocity as you travel. Match the Coriolis effect. It's that simple.
Right, and we represented that as a line.
And the constant force, coupled with the fact that the air mass itself will be pushing you along too, by the way.
In fact, we zoomed in and said that it's going to look like this. Oh, sorry, didn't mean to drag that.
Let me give you a quick.
Hey, wait, real quick. Do me a favor. Draw a line that goes from imagine you're looking at the United States top down, and you're drawing a line from New York to Dallas, like straight west southwest. Draw that line.
Okay.
And then ask Zenick, if you could do that. And you're seeing
so New York's up here, and then Dallas is here.
No, more horizontal, because it would be across America, straight across America, but a little bit slightly south.
You mean like this?
Yeah, like that, but a little bit more down, a little more down. Like
this?
Whatever, 45 degrees, whatever. Yeah, 45 degrees in that angle. Yeah. Okay. So then if we're talking, it starts at 500 miles per hour eastward tangential velocity, and Zenick admits that it would lose that 500 as it's going west southwest, right? Because it's going in the opposite direction of its original conserve momentum. At what point does it gain the 1,000? Or if, let's say that was an angle towards the equator, how does it gain 1,000 miles per hour eastward if there's no angle that it could even aim at that would be directly eastward? I mean, even if you're saying south is somehow closer to east, you're not gonna gain directly backwards tangential velocity when your cruising speed's 500 or 400 or whatever it is. You're gonna have to end up going faster backwards than forwards to keep up with the speed of the Earth. There's no math there that you can say is like working and like some kind of approximation or unnoticeable thing that would happen there, Zanuck. You can't just say it would be so slight because you're going in the opposite direction, losing your original conserved momentum, but needing to gain 500. Impossible. And even if you could do it, even if you were aware of it, when you get to the city that you're aiming at, it's going to continue to go in the opposite direction backwards as you're trying to land on the runway. You'd have to like somehow rotate with the Earth sideways, and none of it works, Zanuck. It's over. No matter how much you give scallop.
Very simply, by slowing the plane down, by not that you can actually turning whether you scrub off tangential velocity or increase velocity. That flight from New York to Dallas, less than a 45-degree angle, close to 45. What do you do along the way? To increase
you're flying straight there, you're not worrying about anything.
Well, let's look at what's the tangential velocity difference between Dallas and New York. Let's find out. You want to calculate it?
Sure, go ahead.
I'm gonna go to bed, bro. I gotta get off here. It's like 3 hours past when I should have went to sleep.
Man.
I got work.
We could have helped your if you want calculations.
I should continue this tomorrow. Yep.
Yo, hey Zeus, that was awesome, man. Thanks for showing up. That was
great. Yeah.
Thanks for walking us through that.
Jesus,
great.
Nice job, man. Seriously, Jesus has the patience of a saint. As weird as that sentence sounds.
Thanks, guys.
Yeah, take care, man. Thanks a lot. Appreciate it.
Have a good night.
A sniper, by the way, right? A sniper that never accounts for Coriolis.
I was not a sniper. No, actually, I was an electro-optics technician.
Oh, okay. I thought you were talking.
So I worked with IR, imaging devices, tracking devices, missile sets, turret sets, stuff like that.
Oh, okay, but they never account for Coriolis when any of that, right?
Bro, I did not learn nothing about no Coriolis. I shot at 500 meters. I didn't shoot no like kilometer shots or nothing like that. But
it would still make a difference.
If you worked in a gunboat and you shot a 16-inch gun, a 50 caliber 16-inch gun, 25 miles, you'd be off by over 100 feet shooting that gun without accounting for Coriolis shooting like yourself.
Mm-hmm.
That's why they have those. The Navy released
all. We got long range shooters that claim there's never been any kind of.
We're talking 26 miles, not 500 yards.
Yeah, dude, you should look into some of the flat Earth videos on how the Navy railgun disproves the curvature of the Earth.
How does it disprove it?
Because the rate at which it's traveling at like, what is it, like 4.5 or 5,500 miles an hour? Some retarded number.
Yeah, it was
some absolutely retarded number. But it's to the point where if they shoot it level, it will literally outpace the drop rate which it will encounter by gravity, and it shoot off into space.
Well, at 17,000 miles, it'll actually levitate, but it just makes it lighter. When you're flying 17,000 miles an hour, which only goes 8, I think the ones that are at down Edwards Air Base, or I think they had 8,000 miles an hour, whatever that was, that little train, an 8,000 mile an hour train. I don't know, Mach 10 or something. Whatever it was, it just becomes lighter. And if it was 17,000 miles an hour, it'd be floating.
Zanuck, I think it'd be more dangerous to be in your plane because you actually are like saying there's corrections to be made rather than being like in a plane where a guy just assumes it's stationary and level and doesn't think about the fact that it might be a spinning ball. But the idea that you like the fact that you have both of these things in your head, like somehow there's adjustments, but he doesn't have to treat it any differently. That's like sounds more dangerous than someone just assumes it's stationary.
It'd be more dangerous to be in a plane with him, but less dangerous if he's shooting at you.
Yeah, exactly. Because he's accounting for shit that's going to make you miss.
Yeah,
right.
we should do the railgun next time. I actually haven't looked at the numbers in forever, so I don't want to like give something too specific and be wrong and talk about stuff I don't know about. But Like,
Well,
I'm pretty sure that the reason is because it shoots so fast that it overpowers the rate of drop it would occur. It would encounter like naturally. You know, like if I level out a rifle and I shoot a rifle leveled out at a target, it's going to experience bullet drop, and you can actually. I mean, every box of ammo that you buy is going to tell you what the bullet drop is at different yardages because it's just a 9.81 meters per second squared, and then times the velocity of that
Yodvos.
round.
It's called Yodvos. You heard of the Yodvos effect?
That might be what it's called, but that's just the velocity of that round. By the time it's the target, you calculate how many seconds it'll be in the air times the gravity, and then you can see how much it drops. Same thing with the railgun, but it shoots so dang fast that it's like going to be flying into space, as far as I know.
No, well, I'm telling you the answer. The answer is that 17,000 you could fly off into space. You could basically orbit around the Earth. If it wasn't for the resistance of the air. But if you're at 10,000 or 8,000, you have to wait. So it'll go farther. Yeah, you're right. But I just posted the Navy Department of Bureau of Ordnance talks about the adjustments to the curvature of Earth and for all these effects, the Yovos as well as the Coriolis effect. But yeah, this is something that is real, and people have to account for their targets. And if you want to fly with me, by the way, I'm the kind of guy that's flying, seeing some mountains in the distance, knowing there's curvature, and even though those mountains are level in front of me, horizontal level right in front of me, they're lower than me. In the maps say they're higher. I know that I'm not high enough because even though it looks like I'm higher than them, when I get closer, they will be too high. By the time I get to them, I will have to make a U-turn. If I try to climb over them, I might not make it and we'll crash. A flat earther might say, you know what? If that's level due to perspective, I'm fine. We're going to try to go over the pass, and those are the guys that are going to die. So you're actually safe with me because I understand the Earth has a curve to it.
See you guys next time.
He's basically admitting
Later,
it's
my
all
friend.
visual.
Peace out, brother.
I left.
Dude, I feel like we all were exhausted by that. That was a long one, boys.
My brain hurts, dude.
That was a long
A good
one.
one,
Yeah,
though.
dude, that got more and more convoluted towards the end there.
None of you explained how biological organisms that actually fly, created by God, work. All your flight models that you just explained are fucking broken and don't explain it. What do you have to say for that? And that's both at flatters and rounders, both of you.
I have to say,
Neither of you have the
vortices,
correct
brother.
model.
Vortices. Shawburger.
That's why I mentioned vortex shearing. It's due to the aether. Period. There's no other explanation for it. How does a flying tank fly? Oh yeah, you can explain wings and planes and ailerons. Big fucking deal.
There was something. So I was watching this one video. They were talking about how they created a vehicle with hollow tubes, and they filled it with this metallic liquid that acted as a sensor and could find where the pressure points of every. It's like as it drove, they could figure out where the pressure was being put on the vehicle as it made turns and everything. And through that, by reverse engineering where the pressure was, they could find out what the best skeletal structure for the vehicle was. Well, they did that with a drone to figure out what the best skeletal structure for a drone would be. And they used AI to reverse engineer it. So they just created a hollowed out drone structure and they flew it around for hours on end, doing all kinds of turns and stuff. And in the hollowed out tubes of the structure of the drone was this metallic liquid that recorded every single little bit of pressure and where it was. Then they used an AI program to reverse engineer what the best, most efficient way to design the drone structure would be. And it came out, the AI spat out a blueprint of what was very, very similar in many aspects to a flying squirrel's skeletal structure. So I don't know if that really relates to what you're talking about.
Comprehend and copy nature. That's the saying right there. So that's what I was getting at.
Yeah,
Nature has given us examples of everything we could possibly think of, including levitation and immortality.
Jellyfish, right?
Correct, as an example. Yep. Or the Amanita muscaria mushroom, mycelium networks.
What were you going to say, Alan?
I was gonna say I posted some pictures to kind of back up what you were saying about the vortex creating lift and stuff. Yeah, the guy Schauberger is famous of I guess the Schauberger turbine, which is apparently a super efficient turbine. It uses like a vortex funnel or whatever to
as well as the shape of the egg. Yep.
Yeah. To do its thing.
It's essentially copying the water cycle. There's a energetic exchange where the water temporarily phase shifts into a plasma and then back. And the cycle repeats. And you can indeed derive energy from that. If you want to get into that, you're going to want to look into getting rotor tech that can do 50,000 RPMs or higher. And stably, of course, which is kind of the difficult part.
Limitless energy. You might know something about this. I heard on this was like a couple, like this was well over a year and a half ago, I think, that I heard this, and so I just kind of lost the episode in my in the history of all the things that I've watched. But I want to say it was a Globebusters episode or something. But it was basically talking about, and I'm gonna probably butcher it, but maybe you can make sense of it since you seem to be well versed in this topic. They were talking about how you could harness free energy and they actually do that with the like the pylons or the electrical poles, just having them run naturally and the cords being up off the ground naturally harnesses the energy from the earth, and we have a free energy system already in effect with the electrical grid.
Oh yeah, 100%. That gets into your radiant energy collectors, gets into atmospheric, electricity, which is to me it's another example of the ether, because everything comes from the ether first.
Can you give me a quick rundown on how those are, if you know anything about those designs? Could you
yes,
kind of
100%
riff on that a little bit? Thank you.
Yeah, if you wouldn't mind just giving books on it. Like, better would be to get my entire collection. Really, I managed to fit it within about 32 gigabytes. If you want to send me a USB drive, I can fill it for you, and then you will basically get back my pretty much my library of Alexander.
So how do they do it though with the is it pylons? Is that the correct term to use?
Or aerials. Some people will call them aerials. It's basically a wire, like you said, which becomes an antenna or an inductor. And you capture the positive with one end, and then the earth is the negative. Now, this energy is not like the normal energy that we like to use. It's not at the right voltage. So you do have to do some tricks with it.
Tricks?
Yeah, it's high voltage instead of being like the voltage that we're normally used to, that our homes use. So it needs to be converted before you can use it.
Are you of the mindset that, or the opinion that this is something that is currently being used in our power grid?
It may be being used, but only a little bit. And I don't think on purpose. If it's being
the episode that I was listening to, they were saying that there's like some of the examples I remember them saying where there's houses that are built, like there's entire neighborhoods and they're built, and it would make more sense architecturally and like for the way that the neighborhoods and the building structures are plotted out if they just tore down some of these pylons or some of these massive towers, but they don't. And like there's tons of examples of this. Again, I'm sorry if I'm butchering this. It's going off of like what I remember in these episodes.
I think you're I don't think it's Globebusters. I think actually, it gets into that because I think you're talking about the lost history of Earth, and to make it into the Tartaria idea that basically we used to understand this energy. and we were powering our structures with this knowledge at some point. That I think that's might be what you're talking about.
Okay, maybe. I don't think it was a lost history of flat Earth. I think I would have remembered that. But yeah, anyways, I think the assertion being made in whatever I was watching was that's currently, at least in part, what's contributing to our current power grid.
It's very real. Earth batteries are also real. That's another example, which are essentially using a similar principle, but not generating as much power, and get more potential by having it farther apart. So the higher you go up, and the deeper you go, you're going to get more.
They want this guy. Oops.
Yeah, only issue there is you wouldn't really be able to take that with you, which is why, like Alan was explaining, an engine like water power based on the water cycle with Victor Schauberger is something you could actually take with you and move around compared to an aerial and antennas and pylons and stuff like that. But it is still a very viable option for city and structures that are on the ground.
Yeah, well, definitely would not argue that we're anywhere close to being efficient with our power supply or consumption. As it currently stands. So,
well, getting back into the planes thing as an example, planes don't use the normal transformer windings and whatnot that we use for our homes. They're using a higher frequency instead of 60 hertz, like what we're usually familiar with. That's so that they can use less weight in the part. It does cost a bit more. Do it that way, but in this case, for an airplane, it matters. Any amount of weight reduction that you can achieve is going to be something you're going to want to do.
Where do you stand on the jet fuel hoax?
I would say that if you're talking about like it being able to burn hotter than just regular jet fuel, I would say it's definitely possible given that the jet fuel is infused, say, with nanothermite, as an example.
Well, I don't know if you've heard about the theory that it was making its rounds a little while ago. And I don't really have an opinion. I haven't really looked into it that much. I've just heard a couple other channels I listen to speak about it in passing. But the fact that jet fuel is more or less not even used hardly at all, and that jet propulsion is it operates off of burning oxygen.
Oh, I see. You're talking about. I don't remember what this effect is, but I know what you're talking about, and it has to do with turbines, very specifically, not your usual prop names. Yes, I know what you're talking about.
Yeah, David Wise has on his if you go to his like Stop Look Think or whatever, and he's spoken about it with I've heard him speak on it on a couple different shows, but like I said, I haven't really looked into it. It's not one of those theories that I was just super interested in. Just as somebody, seems like you're interested in the whole the topic of energy and energy.
Oh yeah, definitely. Not necessarily in the respect of planes, but I just think they're stupid personally when we are at this level of technology. I think it's absolutely absurd. I feel like we should have entire boats, flying by now. Like, why do we not have flying fucking aircraft carriers? Like something out of StarCraft with like little drone motherships and shit flying out of it, and mining, and doing all this fucking stupid nonsense work for us. What the fuck are we doing? It's pretty obvious when you start asking.
As technology. Yeah, as technology gets greater and greater, like as we're increasing,
We seem to get
our-
less and less
Yep,
and less.
exactly.
They
Exactly.
just fucking control us more.
You're not the only one that noticed, bro.
Yeah, it really pisses me off. So that's why I did the deep dive when it comes to the energy and healing for the most part. Those two they're basically the prime control factors in our lives. You know, energy being fuel and food. You know, and then health being obviously your life. So, you know, control food, you control people, and control oil, you control nations. And these are, you know, things said by some very powerful people. So I took it seriously and started looking.
Yeah, well, controlling the minds as well.
Really, it is the mind because it all stems from that.
Because oil, yeah, I'm sure you're aware, right? Like it's not like oil is a non-renewable resource that's been known for
Oh
God
yeah,
knows
the
how
whole
long.
idea. It's like a bunch of dead dinosaurs. It's a bunch of bullshit.
Yeah, so the whole idea that, I mean, yeah, they checked those tapped oil wells and found out, oh, they refilled themselves. So every couple of years, you know, so we know that it's not fossil fuels. They've known for a while. So the very fact that that quote is out there, that you control the oil supply, you control the or whatever the quote may be, if it's relating to oil, you know. And actually, there's a lot of shows that still in pop media and popular culture, it's still propagated that lie. So really, I think it boils down to not as much if you control the food or you control it. It's all about controlling minds and perceptions, right?
Of course, yeah, that's where it really stands for. The greatest technology that's kept from us is consciousness.
Yeah. Yeah, but you're kind of speaking tongue in cheek when you say it pisses you off, right? You're not like legitimately pissed off. You're just
Oh
you're just
yeah,
kind of
it develops my passion. In other words, I don't.
yeah, that's a good way to put it.
For it, but it's where my passion comes from.
Yeah, because like I don't know what your whole how you
Well,
view
just like
like the
the idea of like our parents, you know, and everybody getting sick, you know, and different things like that because we're, you know, taught a bunch of, you know, stuff that leads down to, you know, usually big pharma, Rockefeller, you know, and whatnot type of solutions and whatnot, grants that are circular, and whatnot. You start looking into all this stuff and you start thinking about people you care about. And that does, it's very angry. Am I going to go out and become a terrorist and start sabotaging hospitals and shit like that? Of course not. That would be feeding them and doing what they probably want us to do, right? Helping create more chaos. So,
sure,
yeah.
but also, you know, like at least for me, like I definitely I feel you, man. That was like there was definitely a lot of anger and frustration and resentment towards just life in general when I first entered the rabbit hole. The surface layers of the rabbit hole when I started dipping into, you know, obviously the Rockefeller controlled system, all of the ancient bloodlines, the horrible things that go on, all of the deceptions, everything from Sandy Hook, 9/11, you know, you name it, you know, we're all familiar with it. There's a lot of frustration and anger that comes with that. But at least for me, like at the bottom of the rabbit hole, at least where I am now, was like this big like sigh of relief, you know, like the realizing that, you know, there is a higher order, there is a metaphysical nature that is above a much like the real meat and potatoes of this
Yes, it's
reality.
true because we're consenting to all of it. It's what we're getting
Exactly.
back
Well,
to.
and the reality can't. It's not just set up to where we're just getting screwed endlessly. You know what I mean? We have control through our decisions, through our actions. You know, and that's a very positive aspect of it. And when you find out that like you know you have the ability to make life what you want it to be, and that if you gravitate your life, like I always go towards the rice experiment. Have you done the rice experiment? Are you familiar
Oh
with
yeah,
Dr.
also with water, many other things.
Yeah, so the rice experiment is really powerful because I kind of look at that and apply it to, you know, just your life in general. And if you have the power to like for example,
We are the Schrodinger box, essentially.
yeah, and mold, for example, is not necessarily a bad thing. That's what's so great about the rice experiment is that when you're doing that, you're not like stopping evil from happening, right? The mold fungus taking over the rice is a natural process which is beneficial to nature in
Right. It's just
general.
that good stuff
You're
wins.
you're just advocating on the side of you're literally advocating for the rice. You're stepping in and saying, "Hey, nature, can you hold off through the life through my power of love? I would like to advocate for you not to mold on this rice." You know, if you apply that kind of, if you just take that and apply it to your life, your mentality, your overall um, place in this world, like you know, you realize how powerful you are. So if you have a positive outlook and you live in, say, like more of a love based paradigm than a fear based paradigm, then yeah, there's a lot of crazy stuff happening in the world. But just like to the rice, from the rice's perspective, about how all the rice around it can look like it's molding in all the other jars, if you're giving love and attention and sustaining what you want out of life with your love and your positive emotions and your good vibes, you can bring about real change and sustain it and stave off the molding process. Or I guess the analogy would be, you being taken advantage by the Rockefeller system, by the satanic controllers of this realm. And though it may seem like an insurmountable challenge to go up against them, I mean, the Rice experiment proves that you can literally hold off the natural forces of this world to do your
Oh,
bidding.
no doubt. It's proof that we win in the long run.
Exactly.
I believe that, and I
That's
believe
why,
that. And I
yeah, that's
more
why I
than
would say
believe
that.
it, I know it because I feel I'm part of it. And that's where it becomes deterministic, which can modify the experiment.
That's what's
Speaking
up.
of the rice experiment, the fastest organic material to gather bacteria or a fungus is